Okay, hopefully you guys can hear me well. Oh my God, my bad. But hopefully you guys can hear me well. But this is the second day of the Summer 2025 Foundation Cram Series. And hopefully you guys were able to see the first day. If not, we have the YouTube video up on our Night Hacks channel. So you can watch that. Almost about 4 hours long. But Adam taught every topic and did an amazing job. So hopefully that can help you out if you have like any questions about certain topics, about maybe the information that was taught or the questions that were shown. But we're going to get started on day two of the cram series. And so with day two, a quick overview of our topics. We have algorithm analysis one, two, and three, which is like basically figuring out big O runtime, timing questions, and summations. And so, yeah, no, that stuff is awful. But uh, today's a rough day. But afterwards, we have recurrence relations. Everyone knows that one. And then we have sorting algorithms right after. Basically, every sorting algorithm that is important to the FE. And then we have binary trees and binary search trees as one topic together. Basically, just going to talk about those, know how to do insertion, deletion, all that good stuff, rules, and all that. And then finally, AVL trees, which you're if you don't know the ABC method or know how to find a balance factor, hopefully we'll be able to make it easy for you to understand, and you'll understand it pretty easily. But that's about it for the overview. I don't think I missed anything, but I'm gonna give it to Adam now. Thank you.
All right, thank you, AJ. Welcome back, everybody. Seems like third of you decided to come back, eh? I guess I scared everybody away. No, I'm just kidding. I get it. We're all busy, but anyway, thanks for coming back. Thanks for the positive feedback yesterday. I appreciate that a lot. Today's probably the day of any of these 3 days, the content we're all dreading the most. I personally, and I think I could speak for a lot of people here, do not like the algorithm analysis stuff and the recurrence stuff. But unfortunately, it's a part of the exam, and so we should cover it. What was I going to say? Just like yesterday, feel free to unmute yourself and interrupt me or throw a question in the chat if you need to ask me anything. All right, so should we? I guess we should just get right on into it. I'll try to go a little faster today because we did go about an hour over than we had thought last time, but we'll see where we get to. So anyway, algorithm analysis section one. Yippee! What? Get the hard stuff out of the way first, right? Might as well. Okay, so the big thing you need to know about algorithm analysis is something called big O notation. It's basically a notation to simplify an algorithm's runtime. And honestly, the thing you got to look out for the most in evaluating a big O statement is eliminating any constant factors, eliminating any terms that lose significance as and what am I trying to say? Let me say that again. Eliminating any terms that lose significance as the n, or in some of these examples, x becomes larger. So in this first example up here, forget the 4 and forget the x and forget the 1, because the only thing that matters is the x squared. That's what the function is going to behave off of. So the big O would be O of x squared, the worst case runtime. This one, the second one, there's only one big x term, and the biggest one is x squared, the only one, so it'd be x squared as well. Now in this third one, there's two terms with an x, but you always want to do the biggest one. So in this case, it's x to the fourth, and you forget everything else. So the big O runtime is x to the fourth. And then the same thing down here. The biggest x term is not, it's either you choose between constant or factorial. Factorial is a lot bigger. So you would pick the factorial and forget the 5. It doesn't really do anything. It's only going to behave on the factorial term. So the final runtime would be big O of x factorial. By the way, if I am not sharing or you can't hear me, please let me know. But basically, big O is the worst case runtime. The average and best case runtimes, that's more of a CS2 topic, so I wouldn't really worry about that for the FE. Mainly just worry about big O runtime. There's some limitations for this too. I mean, it's not useful for small input sizes and it assumes infinite memory. But I mean, aside from that, this part of algorithm analysis honestly isn't terrible. So are there any questions before we move onward? All right. So the big thing you usually got to do with Big O, remember, is analyze code. And the best way to do this, is look for any loops. That's usually going to be your big factor. Because if there's no loops, it's probably just going to be a constant runtime. So you look at these loops and you see, okay, I have a nested loop here. So in the back of my brain, I'm thinking it's probably going to be n squared. But let's check. So, and again, don't just always assume something. Make sure you look it over a couple times. So this outer for loop, how many times would this run? N times. Good. And then how many times would the inner for loop run? N times as well. So in this specific example, since they're nested for loops, this would be a big O of n squared runtime. But then if it was, if this other for loop here was not inside of another one, let's say it was just two separate for loops, what would the runtime be then? It would technically it would be 2n, but since again you drop the constants, you would just do it with big O of n. Does that make sense? Cool. So you just look for any operations inside the outside of the loops. And so like again, we just reduced down some of the terms like in that example, like we did above here with the 2n example. And if you see any other recursive calls or function calls, that might add onto the runtime as well. But stuff like this, honestly, I don't think is too bad. So any questions with this? All right, cool. Hope this is making sense so far. Now, sometimes you'll get questions where you have to evaluate algorithms. Something like this, where it's like an algorithm it has a worst case runtime of something, and then on this person's computer with this input size, it runs this fast, and then like what's the biggest value it could be. Basically, what you have to do is you let T of n, and T of n is like the big thing for talking about functions for some reason. I don't know why it's T. There's probably a reason for it. So T of n, that's like the overall runtime, would be when you're solving these, there's a constant which you have to find usually. So you usually label it as C, and then you put whatever the big O runtime is. So in this example, it would be Cn cubed, and then you can plug values in and just do some algebra and hopefully figure something out, which you can see they did here. Does that make sense? All right, cool. So we have two questions of this nature to solve. One of them is going to be just kind of, one of them's kind of just like tell me the runtime, and the other one's doing like the math part. And unfortunately, the math ones are really annoying on the foundation exam because guess what? You don't get a calculator. So Guha will always try to throw math tricks at you. So if you have a calculator, or I'm sorry, no, not calculator. If you've taken discrete, it might help a little, but it's hard sometimes. Yeah, no calculators whatsoever are allowed on this exam, unfortunately. So it's kind of killer on some of these foundation exam questions. But anyway, let's get into this first question. Start off with a 5-pointer today. What is the worst case big O runtime for the following function in terms of the input parameter n? You may assume that the array pointed to by the list is of length n. In order to receive full credit, you must use words to explain your reasoning and arrive at the correct answer. Okay, before we even do the reasoning part, what do you think the worst case runtime of this function could be? I see a couple n's. Why are you saying just n? You have an n times j, because it'll go through the whole list. So there's some interesting different answers here. Okay, so this is good. We're getting some variety. If you see a nested for loop or even a triple nested loop, don't all immediately assume n squared, n cubed, etc. You need to be careful here. This one's actually trying to trick you. A couple people got it right. The big O runtime of this function is actually just big O of n. Now, why is that the case? If you think about it here, j is never getting bigger than n. And then you go in this nested for loop here, and I is never getting bigger than j. So if you think about it, in a sense, you could almost write it like this. I is less than j, which is less than n. So since neither of those get bigger than n, it's only going to, worst case, possibly run n times. Does that make sense? Any confusion with this? What do you mean m by n, Daniel? Or two variables in runtime? Yeah, mainly just look at the conditions, because like here, like you can see I is never going to get bigger than j each time. And then j is never going to get bigger than n each time. And because of that, it can't be bigger than n overall. Does that make sense? And the other thing, all of this stuff up here, this is all constant time. There's no looping or anything you have to do. That's just constant check and return statement. So is there any confusion on this? Yeah, so in the worst case, you'd always assume this is true. So the reason Guha listed basically is I or like kind of what I said, I or J can never exceed N, since I will never get bigger than J and J will never get bigger than N, basically what I said. Um Meaning basically the inner for loop never gets ran more than N times total. It's really that simple. This is supposed to be a simple question. It's 5 points, so does that make sense? Um I mean, you might have to code something with an array of not m by n, Sebastian. I don't think you get two different m by n stuff here. You shouldn't. Yeah, you ignore the outer if statement, Jacob, because this is constant time. It can just instantly return an answer. Does that make sense? Really, the big thing you're looking for that could cause the runtime to increase is either loops or function calls, because those will cause more loops or calls to be ran, which will add onto a stack and possibly add on to your runtime. Does that make sense? Are there any other questions with this one? I know this one's kind of a little trippy and hard to understand at first. All right. Any other questions? Sorry also if I'm not explaining this part as well as I did with some of the other stuff. Algorithm analysis is like, probably one of my weakest things. Everyone has their weakest topics, so I'll say that. So the runtime is just open. Here, I'll let you guys read this for 1 second, in case my explanation didn't make sense. Also, that question came from my foundation exam I took. Any confusion with this before we move on? Yeah, that's why I'm like, let me just show this for a second, Zishan. My apologies if I didn't explain this question that well. All right, we all ready to move on? All right. Okay, this one's not going to be fun. An algorithm that processes a grid of R rows and C columns, so basically a matrix, runs in, or 2D array, runs in big O of R log C time It turns out that for the any R by C grid, we can transpose the grid so that it has C rows and R columns instead, and solve the problem on that grid to get the same answer. Fred ran the code with R equals 10 to the sixth and C equals 10 squared, and it took 3 hours to run. Chanel transposed the grid and reran the code with R equals 10 squared and C equals 10 to the sixth to prove to Fred how inefficient his technique was. How long in seconds would we expect Chanel's execution of the code to take? Please answer as a decimal to 2 places. All right, this is not going to be fun. Excuse me. Yeah, no calculator in this kind of question. This is what sucks. So, what we need to do, remember, usually in this kind of question, you would say T of n is equal to C and then whatever's inside of the big O. But we already have a C. So that's already a curveball on this question. Yeah, it's sometimes they abbreviate log just to LG. So instead of that, so I'll just say C times O of whatever, usually. But instead of that, I think it'll be confusing if we have two variables called C. So let's make a variable called, let's call this C in the original, like the usual thing we do. And let's call that one X. Is everyone okay with that? So basically what I'm going to say is T of n equals X times R log C. Is that okay with everybody? Okay. So remember, the way you start solving these now, once you get the formula written down, it's just a matter of plugging and chugging. We have to figure out basically what is the missing value. Because usually these are two-part problems. Like you have to use the first part that's given you that has everything, usually to figure out this x value. And then once you have the x value, you can use it to actually answer this part here, like the second part of the problem. Does that make sense? Okay. So what do we know so far? We know that t of 10 to the sixth and 10 to the 12th for R and C respectively, or not 10 to the 12th, or 10 squared, is equal to some constant x times R was 10 to the sixth times log of 10 squared. Now, this might be a little tricky to do on a calculator. And then also one other thing I forgot to mention. We know that this whole thing took 3 hours to complete. So now, using this information and all of this, we can try and solve for x. And it's not going to be fun. So, what do you think a good first step would be here? We could solve the log. I'm just trying to see what the best approach to do this question is. Let's leave it as hours for now. I say let's leave it as hours. Just give me 1 second here. Okay, I see what we can do. No, the log wouldn't simplify to 2, I don't think. Just because, does it? No, the log, you can't simplify the log to 2. That's not how that works, unfortunately, because this is log base 2. So that would be saying 2 to what power is 10 squared, basically. You could rewrite this if you want. This might help. You could say x times 10 to the sixth is the same thing as log base 2 to what is 100. That might help. I don't know. But you can't cancel out the log right there. Does that make sense? All I changed was this. Does it make sense, Evan, why the log doesn't simplify to two? It's log base two. Everything in with like CS1 stuff, the log base is always two. You can just assume that. Doesn't log of 10 equal 1? What do you mean doesn't log of 10 equal 1, Ellie? Yeah, it's not log base 10. The log base is 2. So this is basically saying 2 to what equals 100. Yeah, there's a way to bring out the 2 from the log. Let's get rid of this form for a minute. I know this might not seem easy enough to a lot of you, but there's something easy we could probably do here. I like what AJ said. Is there a way to bring out, forget this, is there a way we can bring out the 2 from the log? Think about your log rules. Now multiply 2 by the log. Think about what can you do if a log has an exponent? Yes, you can bring it in front of the log. Exactly. So we can rewrite this as x times 10 to the sixth and 10 to the sixth times 2 times log of 10. Does that make sense? Multiplying two different. I thought you meant multiply it on 2 on this thing, Sebastian. Sorry, I got confused what you said. Yeah, it's the same thing. Yeah, so you can just bring down the 2 and then you multiply with everything just using your log rules. So now what we can do is we can easily solve for k now that we have this a little cleaned up. Or I'm sorry, not k, x. We can solve for x. And we know because this is still equal to 3 hours. So what we can do is say, okay, now how do we get x alone? Yeah, we divide everything on both sides by this mess. So we'd say x is equal to 3 hours over 10 to the sixth times 2 times log of 10. Let me make that a little bigger. Is everyone okay with how we got x? Does that make sense? I know this is a little confusing. So you have to think to yourself, can I repeat? Does it make sense how we got x? Jacob? No. Okay. But what's confusing you, Jacob? Sure. So this is what we basically what we did is we would use this formula usually. You say T of n is equal to C times whatever's in the big O. But if we use whatever's in the big O, there's already a variable called C. So instead of C, I'm going to call it X. Or yeah, X. Just because it's going to be confusing. We have two variables called C. That's why I did X. Normally, if this had said something like R log X, I would have just still called this the X I used C. Does that make sense? It still is. No, it's not. Nothing was 10 squared. Well, technically, this is saying the log of 100, yes, but we're using log rules, Emmanuel, just to clean it up. Does that make sense? Yeah, it's the power log rule, basically. This is kind of coming back from algebra, which I think is why college algebra was the prereq to this class. So, okay, so you have to ask yourself now, is this the answer? Are we done? Remember, we had two questions. Usually these are two-parters. This was part one. Because usually part two, you have all of the info. Usually in these types of questions, sometimes you might have to do it the opposite. But usually in these types of questions, you're missing what x is. and you can't solve part two without figuring x. So we basically had to use Fred's information to find the constant. And now that we have the constant, we can use it to figure out Chanel's information. Does that make sense? Okay. So now we have to do it again. So now with part two, we follow a very similar process. T, because now the T values are flipped. These are flip-flopped. T of 10 squared and 10 to the sixth is equal to, normally, and again, it would just be K log, or I'm sorry, K times R log C. Or not K, I'm sorry, X. I meant to use X. So it'll be X times R log C, which is just what we did before. Now let's plug in what we know. We know that we don't know what T of 10 squared and 10 to the sixth is. That's what we're trying to figure out. But what we do know is that X is this mess from up here. So we can just bring that down because it's a constant value. So 3 hours over over two, or what was it? 10 to the sixth. What was it? 6 times 2 times log of 10. And then multiply that with r log c. And in this case, r is 10 squared and c is 10 to the sixth. So it'd be 10 squared times log of 10 to the sixth. Does that make sense how I set this up? Is there any confusion? Okay. Now what do you think? Now we need to figure out what this equals without a calculator. How do you think we can do that? Exactly. Let's do the same thing with the log on the right. Let's bring down this 6. So right now, at the moment, all of this is going to stay the same. Nope, I forgot I have to do it this way. I have a picture there. And then we'll have times 6 times log of 10. Everyone okay with that? All I did was just use the log power rule and bring that down again. Okay, now let's clean this up a little. What is, um, hold on one second. Just making sure I understand this question fully. Yes, that's a good next step. What can we cancel out? Because if you think about it, let me rewrite this. This might help some of you too. This is the same thing as 3 hours times 10 squared. Yeah, this is going to make it a little easier. Times log 10 over 10 to the sixth times 2 times log 10. So is there anything that could cancel? Yes, the log 10s cancel out. Those are gone. What can we do anything with these two, the 10 to the squared and 10 to the sixth? Yeah, we can subtract the exponents just using our exponent rule. So 2 minus 6 is we'd have a 10 to the fourth on the bottom. And then we would have, I wouldn't divide the oh wait, never mind. Yeah, you can do that. So what's 6 divided by 2? You can do that as well. 6 divided by 2 is you'd have a 3 on the top, right? So now we have 3 hours times 3. Everyone okay with that? What I did there? Let me make this smaller. Does it make sense how we cleaned all this up? Okay, cool. So now, what is, let's simplify the top a little more. What is 9, or what is 3 times 3? 3 hours times 3. 9 hours, perfect. 9 hours over 10 to the fourth. Okay, now what we have to do is figure out, okay, what is this number in seconds? Ugh, this is not going to be fun. But what you can do, I don't know how many of you were taught this. There's something called dimensional analysis, basically. Basically, dimensional analysis is converting between different units of time, measurement. temperature, things like that. So basically, the way it works is you just multiply by the different conversions. And then what you want to do is you want to have the thing on the top cancel out, the unit on the top cancel out with the unit on the bottom. So basically, we want to figure out, okay, we have 9 hours. How many minutes are in an hour? Can someone tell me? 60. So every 1 hour, we have 60 minutes. Now we need to convert that to seconds. So then we have to do this again. We want there to be in 1 minute, there are 60 seconds. And then using division rules, we'd lose the hours and we'd lose the minutes. So we would just have seconds. Does that make sense? And then you can do it the other way too if you want to go from second to minutes. It just things would be flip-flop. That's all. You would just divide. So now let's clean this up a little. Oh, I'm running out of room. Add another page. What is someone tell me what is 60 times 60? 3,600. But you have to be careful here actually because basically what happens, you have to remember this number here, this 10 to the fourth is still in this is still in hours here. Does that make sense? We only got rid of the 9 part. It might be helpful to think of it like this. We have all this, but then on the side we have 1 over 10 to the fourth hours. That times this big mess. That's probably just an easier way to think about it. Does that make sense, what I just did there? We knew it was hours because the constant from above, Sebastian, had 3 hours. It equaled 3 hours. So we figured that out from above. Yes, we have to convert the 10 to the fourth as well. So now what we can do is basically sort of clean this up. This is a little messy now. So we know 60 times 60 is 3,600. Yeah, you can just divide by 10 to the fourth at the end. That'll get rid of the hours for you. So right now, let's clean it up. So right now we have 9 times 3,600. Whoa. Times 3,600 hours over, or no, I'm sorry, seconds over, what was it? 10 to the fourth hours. Does that make sense? So if we want to get rid of the hours, we just have to divide by whatever this number is, and that'll get rid of it. So we need to divide by 10 to the fourth. Does that make sense? So this is pretty easy. If we divide by 10 to the fourth, if you think about it, we can just move this decimal. We can, because the decimal for 3,600 is all the way out here, here, and then we can move it. If you divide it by 10 to the fourth, it just moves over to the left 4 decimal places. So basically now we have 9 times 0.3600 seconds. Is everyone okay with that? Okay, and then lastly, you just have to multiply whatever this number is, and just to save time, the final answer is 3.244 seconds. That one's a bit of a mess. I don't love that one, but I wanted to do one. Sorry if it was a little shaky. Are there any other questions on this before we move on? And again, these are usually two-part questions like this. You find the constant and then you use the constant. Any questions? I know you might just need to let this one kind of like jiggle in your brain for a little while. Oh, good. I'm glad to hear you're confident. Yes. In fact, So you know how there's four sections on the FE? Section three is all algorithm analysis every time, or section C rather. Section C is always algorithm analysis, always. Usually, from what I've seen, it's like there's like it could be a range. In fact, where was the thing from yesterday? That's where it said it. Here you go, part C. So usually there's like a recurrence relation, a runtime analysis, and summations. Yeah, I mean, there's multiple ways you can divide the numbers out. I mean, there's multiple ways you can do it. I was just almost honestly following what Guha did in this problem, but there's multiple ways you could do these. If you get the right answer, honestly, that's all that matters. So this is kind of just what we did in Guha's fancier way. Any questions on anything before we move on? Again, sorry if I was a little shaky with those two. That's my weakest part of this whole class, honestly. That and bitwise, those are my two weakest areas. Okay, let's finish, get out of that crap now and move on to something else I know a lot of people hate, but I find them a little fun after a while, once I get the hang of them. Summations, yay. All right, what are summations? Summations are a tool that helps analyzing algorithms that require adding up many numbers. Basically, a summation is just adding, it's almost, you just think about it as a for loop overall. It's just adding a number over and over and over and over again. Because if you had a loop, for example, like for int I equals 1, I is less than 10, actually less than or equal to 10, I plus plus, and then you say, um, let's just say we have a sum up here and it equals 0. And then each time we said sum plus equals I, this is no different than the summation. These are literally the exact same thing. By the way, I cannot write sigmas for my life, so it looks like a weird E. Of I equals 1 to 10 of I. Those are literally the exact same thing. So if it helps you, you can think of a summation as a for loop. Isn't that pretty cool? And that's something I was going to point out too, Emmanuel. On the foundation exam, as I mentioned yesterday kind of quickly, oops, I did not mean to open that. You are given this formula sheet here, which not only has some functions and how they work, but all the way at the bottom are your summation formulas. So you don't have to memorize those. And if you need to use one that's not there, it'll show you what it is on the test. So that's always good. I guess that's the counter to not getting a calculator, although personally, I'd rather get a calculator and remember the summation formulas. But anyway, isn't that cool with the for loop thing? Those are literally the exact same thing. So basically, to evaluate a summation, you just kind of work on the inside and work your way out. And there's different techniques you can do to evaluate the closed form using these formulas. All it is just following the formulas. And there's two techniques. If you could either split it up, which is very useful. If you have something like this, or even something like this up here, you could split this up into two different summations and apply the same thing, the same outer summation on these two terms. Does that make sense? And now the only other thing you have to worry about too is if the summation, the bottom summation doesn't start at 1, you have to apply what's called a shift and basically start at 1 and then get like the whole range and then subtract out the range that you don't need to get the range you actually want. Basically, if you have something like this, the summation of I equals 3 to 10 of I, the way you would solve that is basically saying, okay, I want the summation of I equals 1 to 10 of I, and I want to subtract it with the summation of I equals 1 to 2 of I. Because if you think about it, if you have a number line from 1 to 10, and these are your I values basically. So if you have 1 here and 10 out here, the let me make the orange summation gets the whole thing. This pink summation here, oh no, I'm sorry. Let me say that again. That's not right. We want the orange summation. That's what we're trying to get. So if this is 3 here, we want to figure out all of this. But the pink summation, we can't apply the formulas like this because it doesn't start at 1. So what we can do is use a shifting technique and have the pink summation figure out the whole thing and then subtract out a summation from 1 to 1 less than the starting index of what we want, or 3 in this case. So if you think about it, if we have this, I need a different color. We do yellow. The yellow summation here is getting this portion here. So if you take the pink and subtract out the yellow, you get the orange, which is what you want. Does that make sense? That's kind of how I like to think about how shifting works. So those are the two main techniques you can do to get apply the formulas. Um, Series I'm not really going to talk about because I don't see them that often. In fact, I don't even recall ever seeing them on a foundation exam. But basically, there's just two different series types that you might see: arithmetic versus geometric series. An arithmetic series is a summation, but each time terms are being added by a same difference. And then a geometric series is that terms are being added, or I'm sorry, multiplied together by a common number. Thank you for the explanation, or the comment about the explanation. Does anyone want me to really cover this part? Because I mean, it's not as important as the other stuff. And these are on that formula sheet if you need them. Okay, I have one. If I get two more no's, I'll skip this. I love as soon as I said that, you all just type no. Is that a basketball? What is that? It's possible, but I honestly have never seen a question with these. So I wouldn't worry. I've seen these questions in discrete, like an intro to discrete, but that's not on the exam anymore. So I wouldn't worry about it, honestly. If you have extra time, maybe if you feel confident on everything else, maybe then you can look this over. But anyway, let's solve some summation questions now. Let's do an easy one and a hard one. Okay. What happened to the picture here? Jeez. Like, yeah, those aren't something like you have to know. If you don't know that, you'd be fine. Okay, here we go. Determine a closed form solution to the following summation in terms of n. Simplify your answer to a standard polynomial form that's not factored. Okay, how do you think we want to begin this here? Can we just solve it? Well, really, you can just ask yourself three questions. Can we solve it? Do we need to apply a shift or do we need to apply a split? Yes, we should split it to two because we don't want to apply the same summation on two terms. Split it up and have two separate summations. It'll be a lot easier. So basically, we can split this up. We'll have two. Please behave, iPad. We'll have two summations. We'll have I equals 1 to 3n of 2i. And then you keep, by the way, you keep this part, the operator the same. So if this was a minus, you would put a minus. What I'm about to put plus. Then in this case, plus another summation with the same terms on the outside. Come on, jeez. And then we bring the 5 down. Does that make sense how I split it up? All right, cool. Okay, so now let's solve this one first. I think this one's going to be easier. Since we're just using a constant here, what does that equal to? It's very simple. Yeah, 5 times 3 to the n. Just copying this down. It's 5 times 3 to the n. You just multiply whatever the constant is by the upper bound, because that's how many times it'll run. Or you could just simplify that right away to 15n. If you think about it, so this is this, I'll just write a side note here. This goes to 5 times 3n, which equals 15n. Does that make sense? Okay, it seems like it makes sense. So now let's keep going. How could I solve this first summation to the left, or not first, the other summation? Exactly. You can move out the 2 because is the 2 being changed at all at any time? No. So you can multiply the 2 by the whole summation. So this now becomes 2 of the summation of I equals 1 times 3n of I plus 15n. And now what can I do? Any ideas? Think back to the formulas now. Yeah. Yeah, you can take out any variable that isn't being changed. Be careful, Zishan. It doesn't become 3n. If this was a if this was a 1, it would be 3n. You have to, since it's the variable that's changing is in the summation. You can't just plug it in a constant. You have to use this formula here. Or sorry, this, come on, go away. This formula here. So as some of you said, the summation itself without the 2 simplifies to 3n times 3n plus 1 over 2. But then you have to remember the whole thing's being multiplied by this 2 outside. And then we're adding that to 15n. Does that make sense to everybody? Cool. And now, as Evan said, these 2's are going to cancel. So this simplifies to 3n times 3n plus 1 plus 15n. Now what do? I distribute, right? Let's distribute this 3n to these other two terms. What's 3n times 3n? 9n squared. Perfect. And then what's 3n times 1? It's just 3n. So you're left with 3n, and then you solve the 15n over here. And now lastly, you can combine like terms, getting a final answer of 9n squared plus 18n. And you could, if you wanted to, factor out a 9, but he asked you at the top to not factor it. So this would be your final answer. Any confusion or questions there? This one's not too bad. All right, cool. Yeah, that one's easy. I like that one. All right, let's do. Yeah, so the formula used, yeah, I'll just write it here. The formula used if you have a summation of I equals 1 to n of I is equal to n times n plus 1 over 2. And there's a proof behind that, but let's be honest, nobody likes proofs of formulas. No problem. And again, you're given these formulas on the exam in fact, I should have put this to the side. In fact, I might do that for the next question. You're given all these formulas. Actually, you know what? I have a better idea. Let me just put this in here. There we go, copy. Now we can put it in this next question. So there's what we just did, basically. Okay, let's put these. I don't, do we need these in this question? Yeah, we will. Okay, I'll put it up here. Up, let me shrink it. Okay, whatever, I'll cover up section C. Okay, ready for a hard one? Let's do it. Determine a closed form solution to the following summation in terms of n. Please leave your answer in factored form. Specifically, your answer should be in this form. And my stylus just died? What happened? Weird, why isn't the laser pointer working? There we go. In this form here, this form, where A, B, C, and D are all integers. Ugh. Yeah, gulp is right. All right. What do we think a good first step is going to be just looking at this? And here's the formulas again. Should we apply a formula, shift, or split? Yeah, we should solve, apply a formula. If you have a nested summation like this, always work with the inner one, in this case, the rightmost one. So which formula can we use on this? Yeah, we can use this one. It's the same thing. Instead of I, it's just J. So now what is this going to become? The summation of I equals 1 to n, but now what's the term on the inside going to be? Yes, oops, I times I plus 1 over 2. Does everyone understand how we did that and why I'm doing I and not n? Okay, cool. Yeah, because I is the upper limit. You do on the upper limit. Exactly. Okay. Now what do you think a good next step is going to be? Yes, we can distribute. Yeah, let's do what Gabriel said. Let's factor out the one half that's there. So now, because the one half isn't being multiplied by anything. So now you're going to have one half times I, oh, why made it so big? I times I plus one. Oh, that's why I made it so big for the summation. Doy. My bad. So you have one half times the summation of I equals 1 to n of I times I plus 1. There we go. Okay, now what can I do? Yes, let's distribute the I. Perfect. So now you get 1 half times the summation of I equals 1 to n of, so we're distributing this I, of I squared plus I. Now what do I want to do? Now we want to split it. Perfect. So we're going to get 1 half times the summation of I equals 1 to n of I squared. And then what operator am I going to put between the summations? Plus, exactly. You just bring the same one down. Plus the summation of I equals 1 to n of I. I keep doing that. I got to move this to the left. That's better. Of I. Any questions so far before we keep going? We finished J up here, Nick. In this summation, we applied this formula to the J summation, and we were done with it all right away. Okay, so now let's take care of this summation first. Well, honestly, tell me this. Aren't there formulas for both of these? Yeah, let's just apply the formulas to them both. Okay, the first one on the left, based on the formula, goes to n, and the upper bound's n, so it's n times n plus 1 over 2n plus 1 all over 6 plus, now let's do the other one. This is just the easy one again. N times n plus 1 over 2. And as you can see, sometimes you have to use these summation formulas more than once. Okay, what do we want to do next? Yeah, let's get a common denominator on the inside. Yeah, forget the one half. We'll deal with that later. Just work on the inside. So now let's get a common denominator. What's the common denominator that 2 and 6 can become? 6, right? So we multiply, as Sebastian said, we can multiply this by 3 to get the common denominator of 6. So now we would have 1 half times this mess all over 6, and then plus 3n times n plus 1 all over 6. Everyone okay with that? And now what I'm going to do is just put that all over one giant 6 so it's less messy. So we'll have n times n plus 1 times 2n plus 1 plus 3n times n plus 1 all over 6. Okay, let's get rid of the 1 half now. The question wants you to have a final answer in this form. So we need to work to that form. You mean down or down here? Actually, forget the 1 half. I don't know why I keep thinking about the 1 half. Let's just plug and chug now on the inside. Oops. All right, so what can we do now, do you think? Multiply what? And like mass distribute what? Actually, you know what? I shouldn't have done this step, even though it's the same thing. I think going back here, what can we do? This might make it a little easier. Can we distribute the 1/2? Because it's being multiplied? Yeah, let's distribute the 1/2. Let's get it out of the way. So this becomes n times n plus 1 times 2n plus 1, and then plus 3n times n plus 1, all both of these over 3. Do you need the formulas again? Is that what you want to see? Oh, whoops, 12. Yeah, doy. My bad. So yeah, now we can clean this up a little. So on the right, the left is going to stay the same over 12, but the right's going to become n times n plus 1 over 4. Everyone okay with that? Okay, we're getting there. Looks like we're starting to get close. I think now what we ought to do is distribute something, don't you? We could have added both the fractions. I mean, do you want to do that? We can go back to that, Zishan, if everyone else is okay with that, going back up here and adding the two fractions. You could do that. Okay, see how I do it. Yeah, so let's distribute the ends. So on the left, well, hold on a second. God, this is such a weird question. Why did he? Oh, that's why. Okay. Yeah. Look what's on both of these. There's an n and an n plus 1. So we could well, we don't really want to factor that out though, because again, we want to stay in this form at the end. It has to be in this form. Let's distribute the ends. I think that'll make the most sense. So we get n squared. Actually, let me do that. Let's just do this one. So we get n squared plus n over 4. I think we might have messed up somewhere, honestly. Yeah, this is why I think we did something wrong. Why did he? Hold on one second. Yes, he. This is weird. Did he split it up or something? Is he? Oh. Oh, okay. I get it. Okay. I'm sorry this is so confusing. Let's go all the way back to when we plugged in the formulas. We clearly got lost along the way. My apologies. This is why I don't love these questions. Okay. What we ought to do is we should deal with the 1/2 for a second. If we multiplied by 1/2, what would we get as a common term? We'd get um, this whole thing, n times n plus 1 times 2n plus 1 over 12 plus n times n plus 1 over 4. Now, what we ought to do is get a common denominator. So we're going to multiply the right side by 3. Plus 3n times n plus 1 over 12. Now what can I do? No, don't combine fractions. Think differently. Can I factor something out? You can't factor out n plus 1. You can factor out a 1/12. Exactly. Because if we factor out a 1/12, it'll make it a lot easier to get into the form that we need to get to. Because both of these terms are being multiplied by 1/12. So on the outside, we'll have 1/12 now, multiplied by n times n plus 1 times 2n plus 1, that whole mess, plus 3n times n plus 1. Okay, does that make sense what I did there? Okay, cool. Okay, now it's smooth sailing. Now, as you both said, now what can we factor out? You can factor out an n times n plus 1, exactly. Because this has an n times n plus 1, and this has an n times n plus 1. So now this becomes n times n plus 1 over 12 times 2n plus 1 plus 3. Everyone okay with that? You could have. I wanted to make sure we didn't mess up again. Okay, now let's finish this stupid thing. So now let's evaluate what can I simplify in here? 2n plus 4, exactly. So you'll have n times n plus 1 over 12 times 2n plus 4. Okay, what can we do now? Any ideas? We're almost done. Very close. Don't want to multiply because that's going to get us away from this final form we need to be. And let me bring this down. That might help. Our final answer needs to be. Oh, you ever do that? Accidentally copy white space. Your final answer needs to be in this form. Exactly. Over here, we can factor out a 2. So we have n times n plus 1 over 12 times 2 times n plus 2. And now, since this is being multiplied together, what can I do? Exactly. 2/12 is 1/6. So you get n times n plus 1 times n plus 2 over 6. And look at that. That's in the form we want. Yeah, I know it's BS. That's it. Sorry about that mistake. I know this one was a bit of a doozy after we did the formula part. Are there any questions with this? We messed up. We were combining too many terms. That was awful on what I did, Musana, or just the whole question? Okay. You want me to reiterate this? Okay. So what we did here, so we factor out the 1/12, right? And then we saw, looking at these two inner terms, is there anything common we could also factor out? Yes. This term has an n times n plus 1, and this term has an n times n plus 1. It's just being multiplied by a 3. So if we factor out the n times n plus 1, we are left with that. And then we just simplify. Does that make sense, Musana? Okay, cool. Any other questions with that one? Apologies again for the mistake. The points, sure. So five of the points, no, six of the points we're getting here. So if you can do that, that's over half of the points on this question, which is pretty good. So any other questions or confusion before we move on? See why I was confused at first on what he did? Because I was confused, like, I was like, where is there a 4 or a 12? I was really confused at first. It's fine, AJ. Don't worry about it. You know what? It's a learning experience for everybody. All right, any other questions? Again, sorry if that was confusing with the mishap. This is why I don't like the algorithm analysis stuff. It's very easy to mess up. All right, should we move on? All right. Last thing with algorithm analysis, and then it's hopefully more fun stuff. Yeah, if the summation starts with 0, you got to just do a teeny little thing. Yes, we are going to get to do recurrence relations. Oh boy, everyone's favorite. And we're going to get to do two of them, Daniel, not just one. I know a lot of you hate these, but you'll get to see the way how I like to solve these. And hopefully it'll make a little more sense to you. Okay. What are recurrence relations? It's basically just a way to determine runtime for recursive functions since there's no loops that are easily identifiable. Basically, it's the same as recursive functions. It includes a base case and a recursive step. And you figure out the way these are derived a little more in CS2 if you need to take. Well, if you're all FE people, you're going to take CS2. Never mind. You'll learn a little more about that in CS2. But basically, the way of solving these is performing a minimum of 3 operations in addition to the initial one, so 4 total. And then finding a general pattern using the base case. This shouldn't say k equals to 1. Usually it is. It's equal to 1, but sometimes it could be equal to something else. Using the base case to simplify it, and then using the k value you find, like the constant in each problem or in each iteration, you can use that to simplify and then get a final answer using basically the techniques we did at the beginning, which is getting rid of constants and stuff. Does that make sense? Okay. By the way, here, AJ, before we get into this, just for a quick breather, just curious, how many of you are from Ahmed and how many of you are from different class? And if you didn't take it with Ahmed, who'd you take it with? Okay, mostly Ahmed. Glad to see that. And Paredes, I figured that. Hey, I remember some of your names. Oh, you were in the Mead Ahmed combination. Ugh, I'm sorry you had to deal with that. Can't imagine what that was like. Okay, anyway, just curious about that. So yeah, he's just showing you the steps here. So yeah, at the end, you get something like this. You get something like this, and you see, okay, it's just order n. Hopefully you remember this from class a little. But now, are there any questions before we get into it? Because I think you understand like the general idea. It's just doing it that's messy. All right. Always, always, always do three additional iterations other than the one that's given you. So make sure you always do a total of four if you include the one that's given. That'll give you half more of the partial credit, apparently. I didn't even know that till right now. So, are you ready for this? No, unfortunately, Masana. Some of them you just have to use a summation. There's no other way to express it. It's unfortunate. Some of them directly ask you to use summations, and some of them you have to pick it out on your own. And one of them we will be doing, you have to pick it on your own. And actually, it's the one from my foundation exam. All right, so we're going to do an exact closed form solution, and apparently the one that was on my exam was evil, according to the Night Hacks team. So let's just do them. Ready for this? Ugh, I messed up this picture. I don't see the answer. All right, let's do this thing. Let's make, oops, let's make a line here. Just so, I don't know if this was covered in Paredes class, but it's helpful to have something called a side note, which is where you kind of like do steps in between. It's not a, I guess it kind of is a table. Okay, so let's see. Use the iteration technique to find an exact closed form solution to the recurrence relation defined below for all positive integers n. T of n equals 2t of n minus 1 plus 5 for all integers n greater than or equal to 2. Please explicitly show the work for the first three iterations, excuse me, before attempting to find the form for like the kth form, followed by arriving at the closed form. Hint, your answer should be of the form t of n equals a times b to the n plus c, where a, b, and c are all integers. So this one's not asking you for a big O answer. Sometimes they do, sometimes you don't. You have to look out for that. Okay, are we ready for this? All right, here's how I like to do this. And this is why I like doing this on the iPad. Color coding, in my opinion, really helps here. But unfortunately, you can't do that on the exam. Okay, so what I like to do, even though it's already there, I write down the same T of n relationship that's already there and mark it with a 1. So T of n is equal to 2t of n minus 1 plus 5. So basically, all I did was just copy down what was up here. That's literally all I did. I just find it easier to have it down there already with the other stuff. Okay, so now what do we need to do? We need to find what t of n minus 1 is, right? So now I'm going to go over to the side note. T of n minus 1, and then what you do is anywhere up in the original t of n, you see n minus 1, or sorry, you see an n, you plug in an n minus 1. The way I like to think of it is, if you have like, think about like in algebra class, if you have f of x equals x squared, and you want to find f of 3, anywhere you see an x, you're going to plug in a 3. So it'd be 3 squared. So it's the same kind of idea. Anywhere you see an n, now I'm going to plug in an n minus 1. Does that make sense? Okay, so let's do that. So 2t of, so I see an n, so I'm going to put an n minus 1 minus this one plus 5. Now let's simplify this. Oh, come on. So this becomes 2t of n minus 2 plus 5. Everyone okay with that? Okay. Now what I like to do, this is where the iPad is like doing this on a, not an iPad, just somewhere on something that does multiple colors. I do this squiggly line a different color. What did the second? No, so I'm plugging in an n minus 1 for n, Daniel. So then this minus 1 is left over. So you have two minus 1s inside the parentheses. Again, this is where I'm kind of trying to say, wherever you see an x, you plug a 3 in. So wherever I see an n, I'm plugging in an n minus 1 now. So you have n minus 1, and then you have this minus 1 left over. Does that make sense? Okay, cool. So what I like to do is make a squiggly line in a different color to signify, okay, I'm bringing that over, and now I'm going to do it in blue, just to keep track of things. So now we're starting on iteration 2, but now, so we have t of n is equal to, we have this 2 from above, which is in black. Now we're multiplying that by t of n minus 1, which we found over here is this in blue. So it's being multiplied by 2t of n minus 2 plus 5. And then you can't forget the 5 from above that was in black. So then you have to add that onto the outside. Does that make sense what I've done so far? Okay, cool. So now let's clean this up. This simplifies, we can distribute this too. So what this simplifies to is 4t of n minus 4 plus 10. But then, can't forget this 5 out here, plus 5. Now we can combine like terms. Yes, it does. Sorry, that should not. This is still n minus 2. Yeah, sorry, it should be n minus 2. Good catch, Zishan. So what happens when you're trying to go fast? So now you get 4t of n minus 2 plus 15. And that's the second iteration. Does that make sense? Okay, cool. I didn't realize until right now. I thought that when they meant 3 iterations, that this was like the 0th iteration. This counts as the first iteration here. So we only have to do the side note thing one more time. Does that make sense, everybody? Okay, cool. I just want to clarify that. I mean, you could do 4, it never hurts. It's up to you, personal preference. If you don't see a pattern, do as many as, well, don't do 20 iterations, but do 3 or 4 or 5. Do as many as you need to do. So now let's do the third iteration. So we need to figure out what t of n minus 2 is now. So now we're going to go back over here to the side note, and I'm going to keep the same color. T of n minus 2 is now, and again, we're going to plug into this guy again. Anywhere I see an n now, I'm going to plug in n minus 2. 2t of n minus 2, and then the minus 1 is just from the original formula, plus 5. Which, if you simplify this, becomes 2t of n minus 3 plus 5. Everyone okay with that, what I did there? Yes. Okay, cool. So now we're going to do a new color. Let's do green. So now over here, iteration 3, we have t of n, oops, is equal to the 4 from the blue times t of n minus 2, which we just figured out is this. So 2t of n minus 3 plus 5. But then you can't forget the 15 from the blue. Now, if you wanted to, you could have left these two terms separate if you had a suspicion there might be a summation. But in this one, I think it's pretty clear that there's not going to be a summation. Usually summations are where there's fractions and stuff. The more you practice with these, you can get better at figuring out, oh, there might be a summation or not. Does that make sense? Okay, cool. So now, again, we'll distribute the 4. So this simplifies to 8t of n minus 3 plus 20 plus 15. Now we simplify that further, we get 8t of n minus 3 plus 35. So now the green iteration is complete, iteration 3. Now, does anyone want me to do a 4th iteration? Or are we ready to move forward to the K part? Okay, let's do the K part now. So now, let's see. what we can say is that T of n, or T at the kth iteration, sorry, I always do this wrong. I like doing it in black. Keep that the same. So T of n, looking at this, if we look back using these on each iteration, what pattern can we get out? Any ideas? Let's just go turn by turn. How does the 8 and the 4 and the 2 correspond to each of these iterations? 2 to the k, exactly. 2 to the kt. Now, how does this number inside this the n part correspond? I'm sorry, here correspond to each of the iterations. N minus k, that one's pretty easy. 2 to the k, t of n minus k. Now, this one's probably going to be a bit of a doozy here. How does 35 relate to 3? And how does 15 relate to 2? And how does 5 relate to 1? Five gets doubled each time. Okay, you're on the right track. Nick, you're close. You're really close. And if you don't think it's right, just write something down and try it. If it's not right, try again. Any other ideas? Yes, Victor has it. It's 5 times 2 to the k minus 1. So if you think about it and just try it, look, if you're on the third iteration, 2 to the k is 8, and then 8 minus 1 is 7, and 7 times 1 is 35. You could do a summation, but why do a summation if you don't need to, Sebastian? More more work and more confusing. So does it make sense how we got this? And it works for these ones up here as well. You can plug it in if you want. So does that make sense to everybody? You just got to think to yourself, okay, yeah, it's kind of creative and clever. I mean, like Sebastian said, you could do a summation, but how to figure it out in the test, you just kind of think about what Victor said. It's going from 5 to 15 to 35. There's this weird jump here. So there's clearly some multiplication going on and some, um, what's it called? Exponential. Basically, just go try plugging things in. If they work, great. If not, if you're getting close, you just got to tweak it a little. Or again, is you could rewrite this as well. You could, as Victor or Sebastian said, you could do a summation of I equals 1 to n, or I'm sorry, k of 2i plus 5. It's the same thing. These both work out to the same number. Actually, wait, no, they don't. I don't know how that summation would work here, Sebastian, on the third iteration. I equals 0. Oh, times 5. My bad. Well, you wouldn't want to. I guess or you have to keep it. Well, you could do it at 0, I guess. Again, I don't know why you would do this technically if you don't have to. It's a little more confusing. But yes, this would work because it works on the second iteration. I don't know. It's up to you, honestly. But let's just focus on it with this. Everyone okay with that? You do either or. So can we move on now? Is everyone okay with this? What we've done so far? Yes. So now let's figure out what k is using the base case that t of 1 is 1. So base case. So t of 1 is equal to 1, and we know that t of n minus k we need to use these basically. So basically we have to set n minus k equal to 1, because using the base case. So if n minus k is equal to 1, what would k be? N minus 1. Exactly. Because what you do is you add k to the other side and get n equals 1 plus k, and then you bring the 1 to the other side and get n minus 1 is equal to k. So the side note, I mean, it honestly depends. Like when I TA'd for Ahmed, if you didn't show the side note on the final exam, you lost points. On this question, it doesn't say anything about quote unquote showing the side notes, but I think it's helpful to have the side note. I think it's confusing to have all of this mixed in over here, in my opinion. But doing all of this, that's half of the points right there, basically. It's 4 points. So it's about half. So anyway, now we know what K is. Excuse me. Let me add another page so we don't run out of room. So now using this, anywhere I see a K up here, I'm going to plug in n minus 1, right? That's just how you use it. So with this, now you can do T of n is equal to 2 times n minus 1. And again, I'm just plugging in n minus 1 wherever I see a K. And now that we use the base case, that just becomes T of 1. Always use the base case there. Plus 5 times 2 to the n minus 1 minus 1. So now let's get rid of the T of 1. So T of n equals, we know T of 1 is 1, so it's just going to equal 2 to the n minus 1 plus 5 times 2 to the n minus 1 minus 1. Does that make sense how I got from here to here? So now what do you think the next step would be? Yeah, let's distribute the 5. So we'll have T of n equals 2 times n minus 1 plus 5 times 2 to the n minus 1 minus 5. Okay, now what do you think is the next step? We're almost there. Yeah, we can combine like terms. Exactly. So we'd have 6 2 to the n minus 1s minus 5. I should have given myself more space there. There we go. Does that make sense? Is anyone okay? Anyone confused on what we did there? Just want to make sure. Now remember, our final answer has to be in this form. It's another one we have to put in a stupid form. So I forgot to copy T of n. So we have the T of n part, and we have the plus C part. That's the minus 5. How can we get it in that other form? It's really close. What can we do? Be careful. Don't look at the 2 to the n part. Can you do something with 6 so that it relates the 2 somehow? How is 6 related to 2? Exactly. 6 is 3 times 2. So if you do that, 3 times 2 times 2 to the n minus 1, what happens now if I multiply 2 times 2 to the n minus 1? What does it become? Using your exponent rules. Exactly, 2 to the n. So you'd have 3 times 2 to the n minus 5. And look at that, it's in the form we want. So that's the final answer. Any confusion there? Any questions on this question at all? It's a bit misleading that he put a plus here, but then it's actually ended up being a minus. Guhal loves doing that. He loves tripping you up. So, any final questions with this one? Yeah, and I mean, he did that on the other question too up here. Same thing. It said it needed to be n plus a, but then it ended up just being n, which I guess you think about it, there would be n plus 0. But, well, how would multiplying the 6 by 2 to the n minus 1? I don't think you can do that, Sebastian. Can you? Anyone a math nerd in here? Oh, splitting them up. Oh, I see what you're saying, I think. So you'd say do something like this becomes 6 times 2 to the n and then times 2 to the negative 1 minus 5. And then the 2 to the negative 1 goes to the bottom. So that equals 6 over 2 times 2 to the n minus 5. And you get 3 times. Yeah, that works. That works as well. Just two alternate routes. That's all. It's the same answer. That's what you meant, right, Sebastian? Yeah, that works. No problem. Sorry, I was a little confused at first. That's just using exponent rules then. Okay, so any other questions before I move on here? Okay, let's do the quote unquote evil recurrence. I don't know who came up with that. Here's what we did, by the way, in the porting distribution. So if you can get up to the K part in that type of question, that's 6 points. That's pretty good. Anyway, okay, this one was on my foundation exam. I didn't even realize that till today. I cannot tell you how happy I was when I saw this question and that it asked for a big O solution instead of a closed form like that one. I was so happy when I saw that. All right, this one's not going to be fun. Let me just copy. I don't feel like drawing the line again, so I'm just going to copy that from up here. Dang it. Okay, let's do this stupid thing. Oh, don't put it up there. Okay, are we ready for this? I know we're not ready. I know we hate this, but once we get through this question, then it's going to be, we're done with all the algorithm analysis crap. Then it's going to be more fun stuff. All right, let's do it. So again, oh, by the way, did you like my process with the colors and stuff and how I did it? I don't know if it helps you. I just think it works that way. All right, here we go. So again, I'm going to copy down the first iteration that was given to us. T of n is equal to 2t of n over 2 plus n cubed. Okay. Now, before we get into this just comes from experience, but the fact that I see that it's not a constant term here and it's something with like an n, it's a polynomial, there's an alarm bell going off in my brain that we're probably going to get a summation somewhere towards the end. So let's just keep an eye out for that. But anyway, to begin, we need to figure out what t of n over 2 is. So let's do that on the side. T of n over 2, and anywhere you see an n over 2 up here, I'm sorry, anywhere you see an n up here, you're going to plug in an n over 2. It's like the x squared thing again. Can I repeat what, Daniel? So this just comes from experience, but the thing that's kind of like alarming me, see how on the last question, this was just a number, this extra term? But on this question, it's oh crap, I don't want to see the answer. That there's it's like what was it, a polynomial? That just kind of makes an alarm bell go off in my head that like, okay, there's probably going to be a summation somewhere. Okay, so now anywhere I see an n, we're going to plug in an n over 2. So t of n over 2, and again, we're just following this formula, It's 2t of n over 2 all over 2 plus n over 2 cubed. Ugh. All right, so now let's clean that up. What the heck? Oh, never mind. Okay, so we have 2t. So what does the inside simplify to? N over 4. Perfect. And then what would the right side simplify to? Or the right term, rather. N cubed over 8, exactly. Or if you want, see, this is where, if you think there's going to be a summation, if I were you, just leave it like this. Let's leave it as n over 2 cubed. It's okay to do that. Because this is going to make it easier when we get to a summation to be able to find the pattern. Will there ever be a case where it isn't n over 2 or n? What do you mean, Sebastian? Like up here? Or like the n minus 1 up here? It could be. I could see it being, yeah, because like I remember from the class, my class I TA'd for. Let me see really quick on the side here. I'm pretty sure there were some where it was n over 4. Yeah, you would go by n over 3s, and then it's just the same idea. You just got to do it with a different denominator. I'm pretty sure that was there. But anyway, so now we have this iteration done, or the side note done. So we'll mix up the color scheme a little this time. Now let's bring it over to the side and do iteration 2. So from above, we know that T of n is equal to, we have the 2 from the black up top, and then we have what we just found, 2t of n over 4 plus n over 2, come on, cubed. Oh, no, yeah, that's right. Sorry. Why did I put that in? Plus the n cubed from above. Does that make sense what I did there? Any confusion or questions? Okay. So now let's keep going. What's going to be the next step? Could someone tell me? How can I clean this up a little? Yeah, exactly. Let's distribute the 2. So we'll distribute the 2 here and here. So then cleaning this up, this becomes 2, or not 2, sorry, 4t of n over 4. And then what's going to happen with this term if I distribute a 2? Be careful. I'm just making sure I don't mess this up. So we have n cubed over 8 over times 2. N cubed, I'm just seeing what you guys said. N cubed over 2 squared. Oh, 2 on the top? Oh, I see what you're saying. So I think, if I recall, let's just write it out. So it'd be 2 times n over 2 cubed plus n cubed. Now I think it'll be helpful. Yeah, now let's evaluate this. So cleaning that up, this becomes 4t of n over 4 plus 2 times n cubed over 8. Yeah, that's it. Plus n cubed, which this then cleans up to 4t of n over 4 plus, oh, whoops, this should be black, plus n cubed over 4 plus n cubed. Okay, does that make sense to everybody what I did there? Sorry, I just needed to write the two next to it, so that clicked with me. But now see how I'm not going to try and combine these two terms. Leave them alone. Okay, so that's iteration 2. So now we need to do iteration 3. We got to do this one more time. All right. Oh, you know what? Let me see something really quickly. Oh, no, it's there. Never mind. Okay, let's continue. So now let's do iteration 3. This is not going to be fun. So to do our next iteration, what do we need to find? T of what? N over 4, exactly. Okay, so now over here, do the orange, keep the color scheme the same. T of n over 4, and now up top, wherever I see an n, I'm going to plug in n over 4, is equal to 2t of n over 4, let me make it smaller, n over 4 all over 2 plus, and then it was n over 4 cubed. So now, what does this simplify to? Well, 2t of what? N over 8. Good. N over 8 plus n over 4 cubed. Everyone okay with that? Okay. Now let's do green because I don't want to, I was going to do blue, but I don't want to do gator colors because we're knights, not gators. And now, iteration 3. Okay. So we have t of n is equal to, what was it? T of n is equal to 4 from the orange, and then from what we just found on the green, 2t of, oh, oops, no, I messed that up. Sorry. I messed up the color scheme. Right? I mean, I guess does it really matter the color scheme? No, it doesn't. Whatever, it's fine. 2t of n over, so we have, there we go, this is it. There we go. 4 times t, 2t of n over 8. Oh, I did flip it again, whatever. Plus n over 4 cubed. And then we have the n cubed over 4 from the last one, and the n cubed from the original one. Let me fix the color scheme. It's going to bug me. That should be green. This should be orange. There we go. No, this should be. Sorry, I get picky with that kind of stuff. Okay. Why'd you say color, Sebastian? Oh, University of Miami. Yeah, I guess. Well, I guess it was inevitable you're going to represent some other college on this meeting. Okay, so now what are we going to do? Someone tell me. Yeah, let's distribute the 4. So in doing so, we get 4, nope, 8t of n over 8. And now I'm going to do the same thing I did above. We'll have 4 times n over 4 cubed plus n cubed over 4 plus n cubed. And now we can clean this up. 8t of n over 8. Let's do this part again. What does this evaluate to? The n over 4 cubed. Plus 4 times what? Yes, n cubed over 64 plus n cubed over 4 plus n cubed. Now, let's cancel out some terms there. 8t of n over 8 plus what's 4 over 64? 1/16th, perfect. N cubed over 16 plus n cubed over, oh, come on, cubed over 4 plus n cubed. Okay, there's our third iteration. Does anyone want to do a fourth iteration, or can we move on to the kth iteration? Oops. Just trying to give that a little more room. All right, we can move on. There we go. Should have spaced out a little better. Okay. Is this making sense so far? Okay. Glad to hear that. Okay, so now we're going to do k. Okay. So in the kth iteration, I'll do purple. T of k, no, n, is going to equal what? Let's go term by term again. Let's forget these guys for now. Here, how is the 8 related in each iteration? 2 to the k, exactly. 2 to the k of t over what? Exactly, it's n over 2 to the k. Okay, now is the hard part. How on earth can I represent this? Be more specific than series. Yes, you need a summation. It's not 4 to the k, Kane. And it's not. Oh, wait. I'm trying to see what Zishan said. Okay, how about this? So we need a summation. What are the bounds going to be? Think about it. Be careful, guys. Be careful. Okay, let's do the bottom bound. Think about if I is 1. Actually, you know what? Yeah, we need to start it at 0. Let me do the inner term first, actually. Then it'll be a little more clear. How can I represent this in each iteration? Yeah, n cubed. Exactly. Over, I'm going to do 4 to the I. Don't do k because k is used elsewhere. Okay, so now that we've done that, yeah, it's the same thing. Well, not 1 over 4 squared, but you can think of it as 1/4 n cubed. Same difference. Okay, so now think about it. We have to think, what are our bounds going to be? Think about if we plug this into the first iteration. Would we want it to start at 1 or 0? 0. It has to start at 0. Otherwise, it won't work out. And then, how big am I going to want it to be? Try looking at the other two iterations. Do I want it to go to k or k minus 1 or k plus 1? Think about it here. This might give it away. This will give it away. So if right here, think about, in this example, k would be 3. If we use the summation up to k, what would 4 cubed be? It has to be k minus 1. Exactly. Just got to take it slow. So does that make sense how we got the general idea? Okay, lost on the k minus 1 part. So there's two. Yeah, so you're starting. Well, it might not have to be k minus 1. But if you think about it, look, if you do k up here, right now, in the third iteration, k would be 3. So if k was 3 up here, you'd have to include an n cubed over 4 cubed term, which is not existent in this iteration. Does that make sense, Daniel? Slightly? Okay. Basically, in doing k minus, and only going up to k minus 1, you're stopping once you hit this term. If you did one more and went to k, included the kth term, you'd have that n over 64 over here, which you don't want. That's why it's k minus 1. Yeah, exactly. It's like a for loop, sort of. Okay, so what's next? Next up is the base case, right? And the base case, again, is t of 1 equals 1. So in applying the base case, we have that t of 1 is 1. So now what do we have to set equal to 1? What's going to equal 1? N over 2 to the k. Good job. N over 2 to the k. So now, what would k be? K is log n, exactly. Because n would equal 2 to the k, so k equals log base log n. It's log base 2 of that, but I'm not going to write it. Okay, and the other page. We're almost there, guys. We're almost there. Okay. So now this is where it gets really weird. All right, we're almost there. So now anywhere I see a k, I'm going to substitute in log n. So now we have t of n is equal to 2 times log base log n times t of 1, because we use the base case, plus the summation of, oh, yeah, I'll get that in a minute. The summation of I equals 0 to infinity, or what the, no, why'd I do that? I'm gonna get myself to k minus 1, not k minus 1, log n minus 1, log n minus 1 of n cubed over 4 to the I. Okay. Now, if you had to guess right now, how did I get what, Ellie? Because how do you get rid of, how can you get rid of k? Or how can you get k alone? Excuse me. How do you get k alone? To cancel out an exponent, you have to take the log of whatever the number is. Now, you don't use the log rule bringing it to the front, Kane. Because if you did that, you'd have k, you would have k log 2 equals n. Or, I'm sorry. I don't even know what you're, forget that. I got confused. Forget what I just said there. All right, let's just keep going. So now we have this. If you had to guess this second, what do you think the big O is going to be? If you had to guess, just curious. It is n cubed, yes. But let's finish it out. So tell me this. So this just simplifies a little further. We can get rid of t of 1. They get 2 log base n plus this summation. Okay. So now, what can I do here? Can I can I do something with this? Not to 1, be careful. You're on the right track, Kane. To n, exactly. Because remember, this is technically log base 2 of n. Always assume it's base 2. So with your log rules, this would cancel out to n. So you have n plus the summation of I equals 0 to log n minus 1 of n cubed of 4 to I. Okay, now what can I do? Yes, but now what can I do with take out the n cubed? Exactly, because that's not getting placed anywhere. So we have n plus n cubed times the summation of I equals 0 to log n minus 1 times 1 over 4 to the I. Now, can I change this at all? Can I rewrite this 1/4 slightly differently? That's an I, by the way. Exactly. This can become n plus n cubed times the summation of I equals 0 to log n minus 1 of 1 over 4 to the I. Does that make sense to everybody? You don't have to, but you probably get a little more extra partial credit if you did, if you mess something else up. Okay, we're really close now. Now, I think it would help. Let me go grab the summation formulas from above. That picture. Which question was that on? It was on this one. Copy. Or duplicate works too. Nope, that was the last one. Here we are. Do any of these formulas look somewhat similar? Yeah, the x to the I. But look at the bounds. Infinity. That's a problem. But due to some weird thing with the base case that I do not understand, and it's covered in the screen, this is totally something that Guha just does not explain well, in my opinion. Based on using some math rules, T of n would be less than or equal to all of this. And because of that, where'd it go? Because of that, you can change this to be infinity. Yeah, what the hell he is exactly right. It's just something because this can never get as big as something. I don't know. I don't understand it either, I'll be honest with you. But anyway, yeah, it's something with the squeeze theorem and like induction. You don't have to. I think honestly on the exam when I took it, I stopped here and guessed n cubed. I stopped here. But or maybe I might have stopped here actually, but somewhere around here. But I just wanted to show you guys how it ended up, like the formal way, like the full thing. So then in doing so, we can now use the formula and get this would be equal to n plus n cubed of 1 over 1 minus a fourth, which then this simplifies to n plus n cubed of 1 over 3/4 simplifies to 4/3. 4/3. So then this simplifies to n plus 4/3 n cubed, which when you finally finish it out equals big O of n cubed. For big O with log n times. Well, yeah, n log n is a very valid answer. N log n is much bigger than n or log n. But anyway, there's the whole giant mess to this question. I can see why it was labeled as evil. It is kind of evil. The point distribution is here. Look at that. You literally get a point just for writing this down again. So if you can get to the K part, it's pretty good. So If you messed up on the n cube summation but got the right answer, you'd probably lose like a point or two there. That's all. Are there any questions with this before we move on? We have three more topics to cover, I believe, right? Is it three? Yeah, it's three. Okay. But now we're out of the hard part. Any questions on this? I know. Do you want me to put it back up to what I did for a second, or do you want me to leave it on this for a second? That really took 2 hours. My God, you're not kidding. I didn't even realize that. Okay. I think now that your brains have been worked a lot, now we can lighten the load a little. I'm sorry that was this was the part I was not looking forward to, but I wanted to help you guys, so that's why I did it. I'm sorry again if on all this part, those three sections that I made some mistakes and whatnot. I just this stuff is so confusing at times and it's really easy to make mistakes, as you can see. So thanks for bearing with me there. Any questions before we move on to the second half? And we should be able to go much faster. Thanks, Evan. All right, let's do some sorting. I like sorting. Sorting's cool. Sorting makes it a lot easier to solve other problems, which you'll learn in CS2. For those of you, wait, if you're all taking the FE, again, you have to take CS2. When you get to CS2, if you have to solve a complex problem, put this in the back of your head now, you'd be a little bit ahead of the game. Think sorting. Put sorting at the front of your head. See if you can sort to help start an algorithm. That's how a lot of the advanced algorithms work, actually, is with sorting. But the cool thing is with Java, it's built in. It's crazy. In this class, you have to remember how the code for merge and bubble and select and sort or whatever, where then once you get to Java, you can just literally write one line like, hey, this class, please sort this, and it does it. It's so cool. But anyway, you still got to know the important stuff for sorting, so let's get into it. I like sorting. So there's five. Ooh, shoot. That was not covered here, AJ. Okay, AJ, can you make a poll real quick? Make a poll, please. Who here does and doesn't understand what heap sort is? I figured some of you either forgot it or don't remember it. Okay, a lot of you forgot. We can do a refresher because that's important. Because actually on my foundation exam there was a heap sort question. Um, AJ, should I save this for heaps tomorrow or on Thursday, or should I do it now? Part of me thinks I should wait for heap stuff. What do you think? What do you guys think? Okay, we'll do it during the heap stuff on Thursday. Well, yeah, yeah. We'll do heap stuff on Thursday. We can talk about the runtime right now, but I'll show you how it works again on Thursday in our last session. All right, so the there's no review tomorrow. Thursday's the last day. Give everyone a break tomorrow. Thursday will be good too, because then Friday most people don't have class, and you can just study all day for the FE. Anyway, so the five main sorting algorithms, heaps important too, but the five main ones, there's bubble, selection, insertion, merge, and quick. Now the five average me do a mock exam? Oh, jeez. Yes, you guys should do one. Because like as much as I want to help you guys, I don't have time to do a mock exam tomorrow. All right, so there's five. I say there's merge and quick sort too. So there's two main average run times. There's n squared and n log n. Bubble, selection, and insertion are n squared. Merge and quick are n log n. You kind of just have to memorize that. That's kind of just like a memorized thing. So bubble sort, as a really quick refresher, you start on the left and then you work each iteration and have the biggest element keep swapping over and over to the right until it gets there. And in doing so, as bubble sort goes, the sorted order is a good way to know if you're doing bubble sort right. Bulges out from the right side, like a staircase from the right. Does that make sense? So bubble sort's just doing a lot of swapping. And on each iteration, the biggest element bubbles to the right, even though sometimes it might not look like visually anything is changing. You might have to do some swaps. Yeah, everyone's gonna know one of them the best. So, any questions on this? Bubble sort is definitely the slowest of them all, even though it's n squared. Okay. Then remember there's selection sort. Selection sort is the one where at each time you start from the left on each iteration, the leftmost element that's not sorted, you mark it as the quote unquote min. And then you find the minimum value each time. And then with the leftmost one that's not sorted, you swap it with the min. And then in doing so, this one only shows one full iteration. But in doing so, you know how bubble sort bulged out in sorted order from this? Selection sort's the opposite. It'll bulge out in sorted order this way. So that's another self-check that you're doing it right. I was just circling on that example, by the way. That wasn't selection sort. You're good, kid. So then you do this n squared because you did this n times. So it's n squared. Any questions on selection sort real quick? If you need a refresher on sorting algorithms, search the algorithm you want and then put like in 5 minutes on YouTube. There's this guy who explains it really good in like 5 minutes. I forget his name. I forgot what his name was, but that's besides the point. Then insertion sort, remember, is like the book sliding one with like the bookcase. On each iteration, you start at the element at the that index basically, and you slide it to the left and where it needs to go. So like here, 10's the current one, and I see, oh, it needs to go between 23. And like, oh, 5, we need to go between 1 and 10. You just do that over and over again. Let me see this link AJ sent. Yeah, that guy. That's the guy. So you just do that over and over. Any quick questions on insertion sort? Hey, and it does this with swapping, by the way, even though visually it looks like it just moves. Okay. Then merge sort, my personal favorite, recursive, it keeps breaking the array in half each time. And since it's recursive, it works on the left half first. And then when it merges them back together, each time it merges, whether it's 2, 4, 6, or 8 things, whatever it is. This Yeah, AJ, I sent out the day one slides to you yesterday for you to post them. I guess that's why I broke them up, but you can send them later too. You're good, man. You're good. But then it merges them back together from left to right as well. That's just how recursion works. So it would do this half, and then it would start doing this half. Merge sort's really cool because it always works. Any questions on merge sort? Okay. And then quick sort's the weird one with the pivot, where you keep splitting the array into subarrays based on a partition, and you move it to where with just you follow the rules and get the pivot stuff so that basically when quick sort's done, the pivot will be in the element it should be sorted in at the end. Where everything to the left of the this is a good way to also know if you're doing quick sort right. Everything to the left of the pivot when you're done with that recursive call should be smaller than the pivot element, and everything to the right should be bigger. I've seen that question asked a few times. We should have done a quick sort question. I would focus on both, honestly, because we're gonna do a coding question and a I think it's a coding question and a runtime question. No, it's not, but there are coding questions. The quick sort on Ahmed's exam. Do you mean the final exam, Sebastian? Was it the one where it was the three different Like you had three different rows you had to fill out. Was it that? Okay, I know what you're talking about. I could, if you want, towards the end, I can show that maybe. I don't know if I should. Actually, I can't really talk about it as exam material, but I could find something similar to it. Now, tell me this. What are the two things that can cause quicksort to not be stable and run in an n squared time? There's two things. Well, yes, bad pivot, but what makes the pivot be bad? Well, that's what I should say. What makes a bad pivot? Everything, the pivot's basically on the end or duplicates, either or. Both do it. So that's kind of what's being talked about here. Yeah, it basically makes it, if it's at the end, it'll make it a glorified bubble sort. Just the way it works out. So that's why it's n squared. Now here's a cheat sheet. This is from Ahmed's class. Realize I didn't see it. Here with all the run times and stuff. Best, average, worst. I would mainly focus on these two. And then if you have memory left, do a best. Honestly, someone should make a Quizlet of all this. If someone can make a Quizlet of all this for everybody, that would be helpful, I feel like. Oh yeah, and then heap sort, it's always heap sort and merge sort you always know are n log n, guarantee no matter what. Now, I don't know if stability or space complexity is going to be on the exam. That was not taught until I after I took the class. So I don't know. So I mean, it wouldn't hurt to know basically if they're stable or unstable basically. It is, I know it's usually CS2, but Ahmed was talking about it. This is from a CS1 class, so you never know, basically. All right, any questions before I get into problems now? All right, so we're going to do two problems, a merge sort tracing, and then some insertions and runtimes. All right, merge sort's great. I love merge sort. And I think it's also one of the easiest ones to understand. Consider tracing through a merge sort of this array. In the process of the code running, 10 merge operations occur. Assume that when the subarray of odd size gets split into two arrays for recursive calls, the left array is smaller than the right. So when the very first recursive call recurs, it will call the subarray storing the 5 leftmost elements. Show the contents of the whole array right after each of the 10 merge operations occurred. Please show your result in the order of the merge operations. Please fill in all the slots, even if they don't change between iterations. 1 point is awarded for every row that is perfect, and you get a bonus point if you don't get them all, or if you do get them all. So if you don't get them all correct, the max points you get on this question is 9. So let's do this now. So we could see in this array, how many elements are there? Kane, who'd you have? What professor? Interesting. So what we need to do, yes, there's 11 elements. So it says in the question, we have to be careful here. If there's it's a difference of odds, the left half should be smaller than the right. So basically, the first recursive call is going to cut it in half, right? Or in this case, the right half's going to be one bigger. But because of that, yeah, well, yeah, the left array is smaller than the right, basically, if there's an odd difference when it cuts in half. That's what I'm trying to say, AJ. Maybe I should have said that better. But so basically, remember how merge works, or merge sort works. It's going to cut it in half. So imagine that. And then, so these are the 5 leftmost elements, and then there's 6 on the end. And again, since it's odd, it said the left half should be smaller. So then remember, it's going to cut this one in half. So then where would be the middle of this? 2, exactly. So then it would cut this in half. Then it's going to cut, remember, you work to the left, all the way to the left first. So then what would be the midpoint of this one? Yes. No, no, it should be right of 2 because it needs to have the left has to have less elements as it says in the question. What do you mean the left has 3? Because I'm talking about from I'm splitting between I'm just splitting here now. Splitting that up. The blue is like a barrier. Forget the blue. Yeah, the left needs more coal. Oh no, you're right. I'm sorry. Jeez. Brain fart. Good catch. There you go. So yeah, it would split it to the left of 2. Sorry, guys. And then it's going to split it again, right? Now where would it be splitting? Yeah, between 0 and 1. Oops, that meant to be purple. So now you work your way back and start merging, right? And remember, everything, you should never change anything to the right of the blue until you finish everything to the left of the blue. Same thing with the green. Never change anything with the green until you finish everything to the left of the green, and so on. That's a good way visually if you need to see that. So now let's do the first merge. If I merge the purple together, is anything going to change? No. So it would be 13, 18, and then the rest stays the same for now. Okay. Now we're going to merge, get rid of the purple and merge the left of the green to the right of the green up to the blue. What would that look like? Oh, no, no, no. I'm sorry. Sorry. We're just going to merge the green to the blue now because we have to do the right half. The right of the green does not get split because you start at the halfway point and just then keep cutting it in half each time. We cut it in half here, and then we cut it in half here, and then we cut it in half here. Sebastian. Okay. So now, if we're going to merge all the green, this part together, because that's how it works, what would change? Wait, why is it? Is there another split? Am I just being really dumb? It's the left is always okay. Let me just see that again. I just need to visually. So if we split the blue, then half of 4 would be 2. So we split it here, but the left needs to be smaller than the right. So it'd be we're splitting it there, and then we're splitting it here. Yeah, okay, so like this, you guys mean? 19 splits from 11 and 2. Oh. So we had this and then this. 13, 18. Sorry, I just need to visualize that because we have 7 and then cut in half. Yeah, okay, yeah. Sorry, that makes sense. Yeah, 13 and 18 are still together. Sorry. I don't know what happened there. Okay, yeah, you're right. Okay, this is right. So now we're gonna merge. We merged up to the green. Now let's merge up to the orange. Is anything gonna change? Yeah, let me draw it out on the side, AJ. That's a good idea. So 13, 18, 19, 11, 2, 7, 4, 15, 6. Come on. 6, 12, and 1. Yeah. So then we're going to split here. So we have all this. Left plus right divided by 2 is 2. So we're going to split here. But yeah, the left is smaller. And then, yeah, and then we would split here. It's like that, right? Okay. Why is it one more split? Oh, because if left plus right is greater than the middle. God, what is with me today? I think, yeah, it's weird because the left half has to be smaller. Yeah, everything's split because of the recursion. So then it would be, yeah, I know how it is visually. It's just weird because it's odd. It's an odd number and he's flipping it weirdly. To this, 'cause 0 plus 10 is 10. Oh, yeah. So you split it at 5. And then, yeah, usually it would be here, but then it has to go over here. This is just trippy, that's all. And then you split 0 and 4, it would go, it'd be here. So you have to get it, then you split up the left half again. Yeah, odd arrays make this a little confusing to draw out. That's why I'm a little confused, and I apologize for that. It's good we're doing it, though. It's practice for everybody. We'd split here. Yeah, normally we'd split there. I need to see this visually. Then we would split here, and then we'd split here. Okay, is that what you guys were saying? I'm so confused right now. Okay, I have one yes. Yes. Okay, yeah. Duh. Yeah. I was just confused because he was saying this. The left array is smaller than the right. So then everything would be shifted. Or does it? No, it just stays like this, doesn't it? Oh yeah, then another split at 1318. Exactly. So yeah, okay. Now we're smooth sailing. I get it now. Sorry about that. So now, yeah. So visually, the first time, nothing's going to change. I see. Yeah, that's right. That makes sense, Victor. You have to split it one more time. Okay. Sorry about that, everybody. So now let's do this. So the first merge, we're merging these two. Nothing gets changed. Now the second merge, we're going to merge these three. Does anything get changed again? No. Actually, no. And I just said that wrong. We're not merging those three. We're now merging these three. Yeah, the second half gets merged. So what would change here? Sorry, my brain is just off today. To 11, 19, exactly. So you have 13, 18, 2, 11, 19, and then the rest stays the same. Or let me erase where we've done merges. That'll help. So then we did this. Oops. Okay, so now we have to merge this half. So what's going to change here? 2 and 11 merge first. That way it would stay, since they're currently split. How do the two get put? So we did this, and then we're merging this half. Oh, because we did this first. Sorry, guys. this we're all arguing over this. It's really confusing. Should we just draw it out like everything in each break? That might. Okay. I'm so sorry. I really apologize about this. Okay, so we have 5, 6, 7, 8, 9, 10. Okay, let me erase all this. Yeah, it is going to be easier to visualize that way. Okay. I'm just so used to doing it like not with this weirdness. So, okay, so we're going to split at 4. No, 5. Because left plus right over 2 is 5. So we'd have on the left 13, 18, 19, 11, 2, and 7. So we'd have 0, 1, 2, 3, 5. But then we were told the left half has to be smaller than the right half. Because this is going to have 6 and that would have 5. So then the 7 is going to get excluded. Does that make sense to everybody? Okay, so now I'm going to get rid of the 7. And I'll just leave it like this. Okay, so now we're going to do it again. Now where am I going to do the split? Well, I'll deal with the right half later. Yeah, so normally it would be here, but because of that stupid rule, it needs to be here. So we'll split off, and we'll have 13 and 18 with 0 and 1. Make another page. Okay, now we're going to split again. Now this one's pretty easy. 13, 18. That splits off. Okay, now I would merge these two. So what? Nothing gets changed, right? Yeah, it's the same. So now we can go do our first merge. 2, 7, 4. Come on. See, this is why this is like, see, I would have gotten tripped up like this. Okay, so now we go back up here. We have this. Now we got to do this split. So now from 2 to 4, 2 plus 4 is 6. If we divide it by 2, it'd be 3. But now normally, so normally we'd split here, but because of the stupid rule, we have to split it here. So splitting this off, we get 2. Oh, I'm sorry. You know what? I didn't even write the second half first. 19, 11, 2. Now we do that split. So now we go in our two separate ways, and we get on the left we'll have 19, should be 1. Then it's 2, and at the right we'll have 11 and 2 at 3 and 4. Now in my what's going to be what the third merge is or the second merge is going to be where? Exactly. We need to merge 11 and 2, which doesn't sit with me right for some reason. Oh yeah, that's why. Because 19 does can't be merged with anything. So yeah, we split 11 and 2. 11 and 2. Okay, I get it now. Yeah, 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 yeah. So now, yeah, now we're gonna merge these guys. So it'd be flipped, right? So we'd have 2 and 11 get flipped. 13, 18, 19, 2, 11, 7, 4, 15, 6. Okay. Now I think we're gonna get a lot better at this. Now I would merge these three. So it would be what? 2, 11, 19, right? For this. So it would be 13, 18. Yeah, this is right. 2, 11, 19. And we're not changing the right half at all yet because we're still working on the left half. And now that we have all this part merged, all this, now we merge up here. Now for our fourth merge, we're going to have the left half of this array in sorted order. So 2, right, yeah, 2, 11, 13, 18, 19, 7, 4, 15, 6, 12, and 1. Okay. Are we good now so far with all this? This weird mess? I appreciate all of you sticking out with me through this and that confusion. Okay. I have a question. How do you know which one? Well, yeah, every time there's a step, Nicholas, is when you merge, and you can't merge one element, so that's why it doesn't count there. That's why it was tripping me up. I was confused. The drawing helped. See, you can only merge two things. So the recursive call here called merge, and it didn't do anything. So then it would go up here, split this up, and then split this up more, and then merge these two, and then merge the three. Does that make sense? So that's why it's counting. It's very weird. It's because of the left half thing. That's why I was so confused. So now let's do the right half. So we're splitting at 5. So we're going to have 5, 6, 7, 8, 9, 5, 6, 7, 8, 9, 10. We'll have 7, 4, 15, 6. So like this is one like I totally didn't do what I said I should have done yesterday. I was jumping straight into it without really taking this stupid rule into consideration. So now 5 plus 10 is 15. 15 divided by 2 using integer division. We would normally split here, but because of that stupid rule again, we have to split here. So now let's split. We will have two of them here, 7 and 4 with 5 and 6. Now we're going to split these two, which should be purple. And we'll have 7, 4, and 5 and 6. Okay, so now what am I going to merge now? 7 and 4, exactly. Wait, doesn't it split in 3 and 3 parts? What do you mean? Oh, good catch. Yeah, because it's even. You're right. See, yes. See, I missed that again. Yeah, when an odd size. Okay, jeez. See, if you just do not pay attention to the details, you really will get messed up on this exam. Okay, so 7, 4, 15. Thank you. 61. 5, 6, 7, 8, 9, 10. In this one, you need both, Sebastian. You have to count and use the indices. Because you have to know if the sizes odd or even, but then you have to figure out the split. Okay, so now, yeah, you get 7.5, but then you round it down, just because that's just how it works with integers and a computer. So then, now we'll split the left half. Now we're going to have the stupid rule because it's an odd size. So we would split normally at 6, but we have to split at 5 now because of the stupid rule because it's an odd sized array. Okay, okay, okay. We'll have 7 and then 4 and 15. Well, 5. Now, is there going to be a merge here? No. This is going to be a merge. And visually, guess what? It's not going to change. So technically up here, so the left half should never change now, by the way. So now, visually, guess what? This still doesn't change. Now, we're going to go back up here and merge these three. So now what's it going to be? 4, 7, 15, right? You following? Just want to make sure. Okay. Seems like they're kind of died down a little. So 2, 11, 13, 18, 19, 4, 7, 15, 6, 12, 1. 1. Okay, we have three merges left. So now we have to split up this array. So 10 plus 8 is 18, and 18 divided by 2, our split point is on the right of 9. You always go to the right. But because of that stupid rule, since we're splitting an odd-sized array, we have to split it here, so the left half is smaller. So now we're going to have 6 and then 2 and 1. 8, 9. Is there going to be a merge here? No. So now we're going to merge these two. And so it's going to become 1 and 2. I think actually it's supposed to be a 12. I lost the 1. My bad. Yeah, it's 12. I just lost it. Yeah, it's a 12. So yeah, 1 and 12. So now we'll go back up here and do that. 2, 11, 13, 18, 19, 4, 7, 15, 6, 1, 12. Now we're going to merge this. So it becomes 1, 6, 12. 2, 11, 13, 18, 19, 4, 7, 15, 1, 6, 12. That's different. And then lastly, now we're going to merge both of these. And now what would it look like? Wait, is that right? No, I'm sorry. We're going to merge both of these. So it'd be 1, 4, 6, 7, 12, 15. Because then the last merge will merge these two. It's 2, 11, 13, 18, 19, 1, 4, 6, 7, 12, 15. And you know, okay, the left and right half are sorted, so you know it should be done the last merge. There it is. Jesus. Sorry, that rule thing really threw me off, and I think it threw off a lot of you too. I apologize for that major confusion and delay there again. Are there any questions on this now that we seem to understand it? Yeah. Well, normal odd merge sort is fine. It's because of the weird odd size rule thing. That's why I was so confused. Okay. Thank you all again for dealing with my confusion there and staying with it. Any questions before we move on? The normal odd merge sort, so like here, if normally it would be like this. This is what the split would look like. But because of the stupid rule, it's flipped. That's why I was so confused. Because it's not normal. Yeah, if they tell you to do a stupid rule, you have to do the stupid rule. Well, if it doesn't say, you just have to follow the algorithm. It's always to the right. Yeah, exactly. It's just a very stupid question. Well, I mean, it's not stupid. The whole point of this was to trick you, obviously, and see if you could outsmart him, but that was just, that was doozy. So, all right, can we move on now? Hopefully, yeah, total. I know this is spring of 2025. This game might be, it could have been a Mead question, but he was gone by then. So yeah, this is probably a Guha question. All right, so let's do the next question. All right, there's the whole table. Probably going a little bit after 7:30 again, and I apologize for that. All right, so question 2. This one's split up, interestingly enough, for the points. Let's do this part first. List the average case runtime of each of the following sorting algorithms in terms of n, the number of items being sorted. Please provide your big O bounds. What is the average runtime of insertion sorting? Don't go look it up. Just see if you remember. N squared. It's always n squared usually. O of n's O of n's the best case runtime. Oh, insertions. I'm thinking selection sort. Yeah, selection sorts n squared usually. What about selection sort? N squared. Good. Heap sort. N log n. It's always n log n for all three. What about Merge sort and log n. Good job. Always n log n. Always. And then what about quick sort? Average is n log n. Good. Okay, any questions on this portion? This is just kind of memorization. You gotta be careful too. It's asking average, best, or worst. That's why that table's helpful. Okay, now let's do this part. Consider running an insertion sort on the array below. How many swaps will be executed through the duration of the algorithm running on this array shown below? Explain how you got your answer. Okay, let's draw this one out. I think that'll be helpful. So normally, how many is this? 1, 2, 3, 4, 5, 6, 9 things. I'll label these. 0 to 8. Okay. So remember how insertion sort works. Insertion sort's the book sliding one. It would probably, if you count it and because this one is just saying in the key, it's showing show the swaps where each move happens. So if you just pointed out where the swaps are in the drawing, it should be fine. Okay, so remember insertion sort, it's the book sliding one. So you just start at each element and then slide it to the left if it needs to. Does 35 need to, can 35 even go to the left? No, it's there's nowhere 35 can go because you always go insertion to the left. So that doesn't count as a swap. Now we're at 25. Can 25, forget all this. This all works every time. Just forget to the right. Does 25 need to move anywhere to be in sorted order? Yes. How many times? Once. So let's add a, I'll do this. 25 was once. Okay. So now let me write the new array. 25, 35, 15, 29, 39, 22, 9. Come on. 96 and 21. Okay. So now we're starting here. Oh no, I'm sorry, here. Here. How many times does 15 need to move over to the left to be in sorted order? Twice. Good job. So 15 is 2. I'll keep using the same array. So I'll draw it every time. Okay, now we are over. Now we're here. How many times does 29 need to move? Once. Good. So flip these two. Oops. No. Again, if someone had nickels for every time I kept messing up, you'd be rich by now. Okay, we just did that. So now we are here. Does 39 need to move? And if so, how many times? It doesn't move at all. So we don't add it to our sum. How about 22? I have a 4 and a 5. Okay, it's 4. Because 25, 22 should be between 15 and 25, right? So to do that, I need to swap with 39 once. 35, that's 2. 29, that's 3. And 25 is 4. So it's 4. Twenty-two, 25. What was next? I forgot 19. 19. No, I didn't. What am I missing? 39. There's 39, 29, and 20, 35. Okay. 35. Nope, 29. Sorry, I had a brain fart. Okay. That's right, I think, right? Yeah. Yeah, yeah, yeah. Okay, so now what? If we move Oops. 19. How many times does it need to swap to be in its right spot? 5. Good job. This one's the 5. So I have 19, 22, right? Yeah, 25. Now it's 29, 35, and 30. Okay, now we're at 6. How many times does 6 need to move? Okay, I have 7 and 6. It's 7. 1, 2, 3, 4, 5, 6, 7. I need to go all the way to the end. 6 is 7. And this is what I'll do this time, so oh no, I can't do what I want to do. Never mind. So we have 6, 6, 15, 22, nope, 19, 22, 29. I missed one, didn't I? I missed 25, thank you. 29, 35, 39. So now, lastly, where does 21 need to go? How many swaps is that going to take? 5. Good job. It was 21 right there. 21 took 5. Okay, I'm not going to draw that out since we're done. So now all you do, add all of these up, and that's your answer. So you have to do this by hand. 1 plus 2, this is 3. 3 plus 1 is 4. 4 plus 4 is 8. 8 plus 5 is 13. 13 plus 7 is 20. 20 plus 5 is 25, which is the correct answer. 25. All right. Any questions on that question? Yeah, it would be 1, 2, 3, 4, 5 swaps. Any questions before we move on? N? Yes, that's an iteration. Yes. It just nothing changed. All right. Let's keep going. There's the answers we talked about. All right. Now we'll have some more fun. Binary trees and binary search trees. Got all binary trees. Okay. Remember the difference between binary trees and binary search trees. They're both very similar. It's a hierarchical data structure composed of nodes, where each node has at most 2 children, which are referred to as the left and the right child. But now remember the difference between a binary tree and a binary search tree. A binary search tree has a special rule where everything to the left of a current node is smaller and everything to the right of a current node is bigger. But a binary tree, that rule does not apply. So like this is a binary tree, but not a binary search tree. And a binary search tree would be this. Does that make sense? The difference? Okay, that's the main difference. And then binary tree, the operations aren't as good because no matter what, you're gonna have to search every element in the tree because it's not somewhat sorted. In a binary search tree, due to the property of the binary search tree, searching and insertion deletions efficient. It's almost like a binary search. It's log n runtime. The worst case scenario though could be log n. Remember, it's possible a binary search. This was actually on my foundation exam. This could be a worst case question. Oops, 315. Like, what's the draw a binary search tree that's the worst case runtime? This is technically a binary search tree, but if you think about it, what is it really in disguise? What data structure? A linked list, exactly. And because of that, it has a O of n runtime. So does that all make sense there? Cool. Okay. So here's some other properties. The height of a binary tree is defined as the number of edges from the root to the deepest leaf node. And it's also known as the longest path from the root to any of the leaf nodes. The height is also known as the depth. And remember, you can just count how many branches there are and then take one down. That's important. A full binary tree is that all the leaf nodes have two children. Each node is full of children. Where a complete binary tree is all levels are completely full from but the last level. A complete tree must be from left to right. It's important to know the differences. In a balanced binary tree, the height of the left and right subtrees of every node differ by most one. Makes sense, and it's similar. Sure as the height's minimized. And then there's three different traversals you can do to access the tree, which we'll talk about real quick. We talked about these two things. Oh, also, yeah, the left and right subtree of each node must also be a binary search tree, and there's no duplicate nodes. So here's some pictures. This is a valid binary search tree on the left. This is not a valid binary search tree because 8 is to the left of 6. No, I'm sorry, 6 is to the right of 7. And because of that, that violates the property because everything to the left of 7 should be smaller than 7. So this is not true. It doesn't work. This one is not valid because why isn't that valid? Oh, because it's a left child of 2. It's just a weird. The arrow looks weird. Yeah, because the left child is bigger than the current child, which violates the property. 3 needs to be the right child of 2. Does that make sense? All right, cool. So there's 3 traversals you can do: pre-order, in order, and a post-order. Which of the 3 traversals gives you a sorted linked list? Oh, no, sorry, tree. What prints them out all the nodes in sorted order? Which of the 3 traversals? I see someone said in order. What else do people think? Well, I think you can see here it's not pre-order. It's in order, exactly. Remember, pre-order works, pre-order is roots or the current left, right. So go 1, 2, 4, 5, 3, 6. As you can see there. And then there's the code for it. It's basically the same thing. In order does left, root, right. So work its way down and go left, then root, right, 1, 3. What? Why isn't this sorted? The heck? Okay. Yeah, I think it's messed up. Because in order is supposed to print in sorted order, AJ. Yeah, because I think you flipped these 2 slides. Something weird happened here. It's all right. It's all right. Well, no, because it's like, oh, thank you. Thank you. Okay. Thank you, Zishan. That's why. It's not a binary search tree, AJ. That's why. Okay. I was confused. Yeah, because it only prints it out in binary search trees. Duh. Thank you. So yeah, good catch. So yeah, so it would go left, left. It would print the 4, then the 2, then the 5, then the 1, then the 3, then the 6. Okay, everyone clear on that now? Thank you for pointing that out. So then post order goes left, right, root. So it would go 4, 5, 2, 6, 3, 1. And there's the code. Any questions on all the traversing? Okay, and then remember, inserting post order you use when you're freeing memory. If you want to free all the DMA in a binary search tree or binary tree, you have to use post order. Otherwise, you're going to get double freeze or memory leaks. So remember, there's 3 different insertion types. If you're inserting to where it's a leaf, you just put it in. It's easy. If you're inserting to a inner node, oh no, wait, you always insert to the leaf. Never mind. Sorry, I'm thinking of deletion. So yeah, in this case, 40, you trigger your way down to the tree until you hit a leaf. It would go right here to the right of 40. Make sense? It's not that bad. Deletion's what's the killer. Because there's three cases. If you delete a leaf, it just goes away. If you delete a node with a single child, that's pretty easy too. You just bring up that node to where you're getting rid of, and then get rid of that node, the original node. You just swap them basically. And now if you're deleting a node with two children, you take the max from the left subtree or the min from the right subtree. In this example, they're taking the min from the right subtree, which is 60, and they're replacing it with the root, 50 in this case, because that's what we want to delete. And then it still checks out. Any questions on all that? All right, should be hopefully quick review. All right, we're going to do two questions, a tracing question and a coding question. I'm going to give you guys, this is a good one. I'm going to do some recursion trees, which we didn't get to do yesterday. I'll give you guys some time. I'll give you like 5 minutes to try this one on your own, and we can see how we go, how you guys do. Let me make a timer again, like yesterday, and I'll pick a different music this time. I'll do, yeah, let's do pencils down. Okay, I'll give you guys 5 minutes and come back together. There you go. Good luck. All right. What did you all get as the answer? If you even finished it. If you didn't finish it, that's fine. Just tell me. Just curious. 50 is the correct answer. 50. Good job to those who got it. I can understand it seems like a lot. All right, so let's go over this question. I'm about to run over my kid. There we go. Okay, consider the following mystery function that uses a typical tree node structure of a binary tree. This is a binary search tree, it looks like. Just by looking at it, it is. So you have the data and then the left and right. Okay. Int mystery, you're passing in the root. And then we're just going to follow this along. This is going to be really helpful with a recursive tree, I think. So we're passing in, we're calling the function on m. I'm just going to abbreviate it with m of 13. So here's how I like to draw recursive trees. So m of 13, we have, okay. Is the root null? No. Is is the root even? Yes or no? No. So this isn't even going in there. So we're going to return 5 plus the calls on its children. So we'll be doing 5 plus m of 4 plus m of, what was it, 25. Now, because it's recursion, go to the left child first. M of 4. It's not null. Is it even? Yes. So temp is going to equal 3 because it's root left. Root left becomes root right. So now this becomes 8. Does that make sense how I did that? Okay. Well, I did that. And then root right equals 10. It's switching these. And then it's doing the recursive call again on its two children. So now m of 4 is going to call 5 plus m of 8 plus m of 3. Pretty trippy stuff, if you ask me. So now we're going to go to the left first. We're going to do 8. So m of 8. Is 8 null? No. So now, is root data mod 2 equals 0? Yes. So we're doing this weird thing again. Temp is going to be equal to 8. And then we're going to switch these two, it looks like. Which, hold on a second. I hope I'm doing this right. Isn't it swapping the whole node? It's a little branch, not tree. Oh, yeah, good point. That's right. So yeah, these get swapped too. Okay, that makes sense. Sorry. Good catch. Because you're swapping, it's swapping the branch, not just because it's a pointer. Duh. It's not taking the data, it's the pointer. Yeah. So it swaps the both of those. It's a weird question. I just want to make sure again. So this is even, and then so temp becomes 8. I'm back on the 4 call. No, temp was 3. I'm sorry, temp was 3. Now 4's left is going to point to 8. Yeah, so this points to 8, and then root right equals temp. Yeah, okay. Then we go here. So now 8, we're doing this thing again. So yeah, now that's going to switch those. Oh, so the 5's going to be left alone, wouldn't it? Well, we're on M of 8. So temp is 8. And then, oh, 8's even. Duh. Sorry. Yeah, sorry. I just glossed right over that. See, now we're just going to go to the left child. 5 plus M of 5 plus, and this has, I'm just going to write M of nothing there. So now we're on M of 5. What do you mean it's also swapped? Right child 8 of 8 is 5. Left is null. Oh yeah, I see. Yeah, so that's a weird question. Let me draw the tree out here. It's 13. So we have 4. But now we're doing the swap. So this becomes 8. We had 8 and 3. And then, yeah, now this is going to swap. We have 5 and nothing. I see. And then we didn't do this yet. Okay, I see. So now we're here on M of 5. 5 is odd. So we have to do this again. But nothing's going to get swapped, really, right? Because it has no children. So you'd just be swapping null and null, right? Yeah. So now this is just going to return 5 plus m of nothing plus m of nothing. So both of these return 0. Okay, so now we're going to start working our way back up. This returns 5. We go over here, that's 0. Now we have 10. Now we got to take care of this recursive chain. Is 3 even? No. So now it's just going to call 5 plus, whoa, 5 with, seriously? M of, oh, it doesn't have any kids as well. That's easy. Oh no, wait, I forgot the 2. Whoops. The 2 should be wait a second. This is 2. I messed up this tree. This is 2. This is 5. Because we only swapped once. Right? I'm so confused again. Or does it swap the branch? So we swapped 8 and 3, which also causes. We swapped 8 and 3, which also causes. No, yeah, they would be switched. They have to be. Five is still there. Yeah, 5 is there, and then we have 2 on the left, like it was before. Okay, sorry. So we have m of 3. 3 is not odd, so now it's going to do 5 plus m of 2 plus. Come on, man. Oh, great. Just crashed. Oh my God, did it delete everything? I swear to God. Okay. Why did it bring me all the way up there? Okay. Wow, it lost that. Okay, so this was 5. Yeah, and then the 2 was to the left. There we go. So we were at 5 plus m of 2 plus m of nothing. So at m of 2, although it's going to do 5 plus m of nothing plus m of nothing. So this will return 5 because these return 0. This returns 0. So we have 5. Now we're going to have 10. 10 plus 10, we're going to have 20 now. Okay, now we got to do the right tree. Okay, so now we're going over here to the right. Is 25 odd? Yeah, or even no. So this stays the same. And it's going to call m on its 2 children with adding 5. 5 plus m of the left, 20, plus m of 30. So let's take care of this case. It's not null, but it is even, so it's going to swap the 15 to the right. Does everyone see that? This 15 is going to get moved. Whoops. That's my laser pointer. The 15 is going to go to the right side now because 20 is swapping its branch. Does that make sense to everybody? Yes? No? Question mark? Okay. So now we'll have 15 to the right of 20. Like that. So now m of, that's going to return 5 plus m of 15 plus m of nothing. So this is going to return 5 plus m of nothing plus m of nothing. So this gets 5. Now we have 10. It's going to go over here. That's going to be 5 plus m of nothing plus m of nothing. So that's a 5. So we have 20 now, because 15 plus 5 is 20. It's 20%. Uh-oh, I missed a 5 somewhere. Where did I miss the 5? 5 there. All right. 10. 5 plus 15. Where? Oh, no, that's the left tree. Here? 5 plus 10 plus 10. Oh, I see it. Sorry. Yeah, 25 plus 20 plus 5, that's 50. So returns 50. Okay. And that is what the tree is supposed to look like. Oh, I forgot the 30 though. It didn't get changed. Okay. Any questions on that or confusion? Sorry about the confusion with that one again. You can see even the TAs can make mistakes. All right. Any questions before we move on? 3 questions left of the night, and then we'll be done. All right. Yeah, that one was just trippy with the switching. I forgot it switches the branch. So, okay. And there, yeah, there's the answer and what was swapped. Okay. Next up, write a recursive function named sum at depth that takes a pointer to the root of a binary tree, root and a non-negative integer depth, and returns the sum of all the values in the nodes that are at a level depth below the root. For example, if you pass the root of the following binary tree and depth equals 2, the function should return 61 because it's getting everything at the root or at that depth level and adding them up. You may assume that depth is a non-negative integer. You must write your solution in a single function. You cannot call any helper functions. Okay. So, how do you think we're going to do this? Because remember, we have to do this recursively. Yeah, well, we can start. Let's start with our base case. Good idea. So, what's one base case? How do we know to stop traversing? Well, depth equaling 2 is just an example, Jared. Yeah, first let's check if the root is null. Because if the root's null, you can't do anything. If root equals null, what am I going to return? 0. Good. Return 0. Okay. Else, now what? How do we know if we're done traversing? Yeah, our depth is 0. Because think about how we can do this. If we're starting at the root and then we traverse and subtract the depth by 1 each time, if the depth variable is 0, that means we want to add what's at the value there, right? Doesn't that make sense? Anyone else confused on that? Okay, so that's really all it is. So then, else if depth is 0, what am I going to return? That means we want to add in that, yeah, roots data. Roots, arrow, data. And then lastly, otherwise, what am I going to do? Else, if neither of these are true, that means I got to keep going. So then what are my recursive calls going to be? Sum at depth, root left, and then what? What about the depth? Depth minus 1. Good job, Sebastian. And then you just do that with, you add it to the same thing with the right. And that's it. Was this a 5-pointer or a 10-pointer? Wow, this was a 10-pointer. So does it make sense how this works to everybody else? Is there any confusion or questions with this? Yeah, that was very chill. I'm surprised that's a 10-pointer for this code. Any confusion or questions there? Does everyone understand how it works? All right, one more topic. AVL trees. I love AVL trees. Also, for those like Despicable Me, I never thought about this till recently, but if you think about it, you could call AVL trees anti-villainly trees from Despicable Me too. I don't know why someone told me that, and I was like, yeah, you know what? That's stupid, but it's there. Who here's seen Despicable Me too? You know how Lucy works for the Anti-Villain League? The abbreviation of the Anti-Villain League is AVL. This is some stupid brain rot for you to get a quick brain break. Okay. What is an AVL tree? An AVL tree is basically a self-balancing binary search tree. By the way, you'll never have to code one of these. Where the difference between the heights of the left and right subtrees for any node cannot be more than 1. The difference between the heights of the left and right subtree is known as the balance factor, basically. And the example tree is an AVL tree because the heights of the left and right subtrees for every node, the difference is less than or equal to 1. That's all it is. Ellie, who did you have? What professor? Who taught you AVL trees? What professor? Did you not learn the ABC method? Okay. Well, you might be able to. An AVL tree, Jacob, is a self-balancing binary search tree. So anytime you insert or delete a node, it rebalances itself automatically so that it guarantees a logarithmic runtime. Basically, so it doesn't get into, it will never happen to get into a tree that looks like this and cause a O of n runtime. Does that make sense? That's all it does. It ensures the runtime's logarithmic. So there's this thing called the balance factor that each node has. It's calculated by the height of the left subtree and the height of the right subtree. At every node, the balance factor can only have for it to be legal, it can only have -1, 0, or 1. Leaf nodes will always have a balance factor of 0. If you calculate the balance factor of a node and it's not -1, 0, or 1, you have to do some fixing. So tell me, if I'm at 8, what would the balance factor be? Yeah, one because the height of the left subtree is 1 and the height of the right subtree is 0. So 1 minus 0 is 1. Does that make sense? Pretty easy, right? But then what about 12? If you're this one, what's the height of the left subtree? You can't count the nodes. Well, I mean, you could, but because there's one, two, three, four. There's 5 nodes here, but the height is. I wouldn't count the nodes per se. You got to count the branches, and then you can just subtract them. Well, in this case, I'm asking. Oh yeah, well you don't count the root node yet. But yeah, so you can just count the root, the number of nodes then in the subtree and subtract one. That would work. Yeah. So forget what I said. You can do that. So if I'm at 12, what's the balance factor? What's the height of the left subtree? 2, and then what's the height of the right subtree? That's fine at 12, but looking at 8, what's the height of the left subtree? It's 2. Be careful. Remember, this is technically 0. So it'd be 0, 1, 2, minus 0. That's a problem because the balance factor then would be 2. Does that make sense? Okay. The rotations, basically, the way you fix AVL trees, you're implicitly doing a rotation. But there's something cool called the ABC method, which it sounds like some of you have not learned. There's a left rotation, a right rotation. You don't have to worry about the rotations too much. All that matters is that no matter what, you can always late for any of these 4 problems, the 4 options that they could be like, you can label them in sorted order, the 3 nodes that you've circled, and basically it will always work out to this result. You always restructure it like that. So Ellie, was that taught to you? Does that ring a bell? No. Ooh, interesting. I'm about to make this 10,000 times easier for you, I hope. This is so much easier. You don't have to do any rotations. Well, it implies you're actually doing the rotation, but like you don't have to think about it. That's why it's easy. Yeah, the ABC method's great. And then there's this T0, T1, T2, T3 crap. I don't like that. I found a much easier way. I'm just trying to make this as easy as possible because if you get the procedure down, these are cake. So insertion's pretty easy. You insert the node, you start from that node, working your way up to the root. Along the way, at each node, you calculate the balance factor. And if at any point you have a problem, you fix it. And then you keep going up to the root. That's all it is. Same thing for deletion, too. Except deletion, it's just the rules are slightly differently for when you have a problem in insertion and deletion. That's all. So let's do one of each. Ugh, damn questions. Prize is a 5-pointer. I think most people get tripped up on the lead. That's why. All right, Ellie, I'm probably gonna call you out here a couple times, but I want to see if you can understand this. All right, so here we go. Insert the following AVL integers into an AVL tree in inserted order. Whenever an insertion causes the tree to become unbalanced, rebalance it immediately before proceeding with the next insertion. Continuing to this process, rebalancing is needed until all elements have been added. Put a box around the state of the tree after each of the bolded underlined statements or elements are inserted. Each of these pictures is 1 point. Okay, here we go. So we're going to insert 50. What's the balance factor of 50? 0. Because the height of the left subtree is -1. You know what? I'll do this. The height of the left subtree is -1, and the height of the right subtree is -1. So -1 minus -1 is 0. So you're fine. Does that make sense? I hope. Pretty easy. So now we're going to insert 80. Where's it going to go? First off, to the right of 50. Right. So again, now you've inserted a node. Start at that node and work your way up to the root. So I'm at 80. What's the balance factor of 80? You can just know right away, by the way, any leaf node's balance factor is 0. Okay, cool. Now someone else other than Sebastian tell me what's the height, what's the balance factor of 50 now? -1. Be careful. Because the height of the left subtree is -1 and the height of the right subtree is 0. So -1 minus 0 is -1. Makes sense, right? Pretty self-explanatory, I think. Just got to be careful. Now we're going to insert 70. Where's it going to go? Left of 80. Good. So what's the balance factor of 70? 0, because it's a leaf. What's the balance factor of 80? 1, because the height of the left subtree is 0 and the right of the height subtree is -1. So 0 minus -1 is 1. Now 50. What's the height of the left subtree? -1. -1. Be careful. The height of the left subtree of 50 is -1. If nothing exists, it's -1. And then what's the height of the right subtree of 50? It's 1. So what's the balance factor for 50? -2. Does everyone understand how it's -2? No. Okay. So remember, the balance factor is always the height of the left subtree minus the height of the right subtree. So Jacob, what's the height of the left subtree of 50? We're talking about 50. -1. That's just how it works. You always subtract 1. You would think it's 0, but you subtract 1. Anytime you calculate the height, you just subtract 1. I have no idea. That's just how it is. That's how it works for binary search trees too. You have to do -1. That's what I was taught to do. Otherwise, you might get some bad calculations. Well, the height of this technically is supposed to be 1. You're supposed to start at -1. That's just how it is. I don't know why. So the height of the left subtree is -1, Jacob. And then what's the height of the right subtree, Jacob? 1. So -1 minus 1 is -2. Does that make sense, Jacob? Okay. So now is that a problem? Oops. Yes. Oh, I thought that was something. Is that a problem for 50? Yes or no? Can 50's balance factor be -2? No. So yes, that's a problem. So remember how this works. So Ellie, I'm curious how you're going to think of this. So the way you can always restructure this, remember, when you're inserting, if you can counter a node with a problem, you circle the node you're at that has the problem, and then you take 2 steps towards the insertion point. So what would be the next node I'd circle? 80 or 70? You just follow the branches, Ellie. Just follow the branch. I should have said that. You just follow the branch and circle the next 2 nodes going towards the insertion point. So you do 80, and then the last one's 70. Now you label them A, B, and C, with A being less than B, with B being less than C. So who would be A? 50. Who would be B? 70. And C is 80. Now every time, all you have to do is restructure it like this. BAC, like that. And it always works every time. So in doing so, we'll have 70, 50, 80. And then you check again, just do a self-check, make sure you didn't mess up. What's the balance factor of 70? 0, exactly. So this is making sense so far. Okay, now we're going to keep going. So I'll highlight this to say this is our first thing, but now we're going to keep going. Because it wants to know it they want to know it at 70. So now we're going to insert 99. Or I guess I just kind of revealed the answer. Where's it going to go if I put in 99? Be careful. Remember, you have to, yeah, right of 80. You have to keep the binary search tree property. Okay. So now you start at that node you inserted and work your way up to the root. What's the balance factor of 99? Be careful, Jacob. It's 0. The height of the left subtree is -1, and the height of the right subtree is -1. So -1 minus -1 is 0. If you have to, write it out each time. I did that at the beginning when I used to do this. So now we're at 80. You work your way up to the root. Just keep following the branches from the node you inserted. What's the height of the left subtree? Or I'm sorry, what's the balance factor of 80? What's the balance factor of 80? That's what I meant to say. -1. Perfect. Now we're at 70. What's the balance factor of 70? Yes, it's also -1. It's -1. Be careful. The height of the left subtree is 0, and the height of the right subtree is 1. So 0 minus 1 is -1. But we don't have any problems, right? So we're fine. Now we're going to insert 85. Where's it going to go? Good, the left of 99. Now we start working from that node and just follow the branches all the way to the root. So what's the balance factor of 85? You should be able to do this in 2 seconds because it's a leaf node. 0, good. Okay, excuse me. 99, what's the balance factor? 1, good. Everyone okay there? Okay. 80, what's the balance factor? -2. Everyone understand why it's -2? Everyone see that? Okay. Now, is that a problem? Yes. So you just follow the procedure. Circle the node you're at, 80. Now, you follow the branches 2 steps towards where you inserted. So 99, 85, and now you label it A, B, C. Someone tell me who's going to be A, B, and C. Yep. 85 is B, and then C is 99. So now you just convert this into this. And then you leave the rest alone because it's not effective. So now you keep going. So you have 70, 50, and then 85, 80, and 99. And now you do a self-check. What's the balance factor of 85? Did you go back up to the B node you circled? 0. Good. But now am I done checking balance factors right now, or do I need to keep going? Correct. You don't assume you're done. Keep going all the way up to the root. So now I'm going to check 70. What's the balance factor of 70? -1. 0 minus -1. -1. Wait. 0 minus 1 is -1. Sorry. 0 minus 1 is -1. So there's what the tree looks like after inserting 85. Everyone okay so far? I have 1 yes. I have 2 yeses. Okay. Ellie, how are you feeling? Because I know this might be new for you. Good. I'm glad. Do you like this better? Hey, I'm glad to hear that. It's just a lot easier. Okay, so now let's keep going. So now we got to insert 100, I think is what it was. So we have 70, 50, 85, 80. Come on. God. 99. Okay. Yeah, we're inserting 100. So where's it going to go? Right of 99. Perfect. Okay. Now we start the process. Tell me, which nodes am I going to check? How many? 4. It's this path here. is you just start where you insert and check all the nodes up to the root on the branches. So, what's the balance factor of 100? 0. Good. It's always 0 if it's a leaf node. Always. What's the balance factor of 99? -1. Good. Somebody else other than Sebastian, what's the balance factor of 85? -1. Good. What's the balance factor of 70? Careful. It's -2. Because this height is 0 and this height is 2. So 0 minus 2 is -2. Does that make sense, Alfredo? So we have a problem. So I'm going to circle 70 because that's the problem. Now, here, Ellie, which two nodes am I going to circle now? '85, good. And then 99. Yes, because you keep just go following the branches to where you inserted. Keep going on that path. So now who's going to be my A? 70. Who's B? Yeah, 85, 99. Now, okay. So this, who here knows the T0, T1, T2, T3 thing, like the subtrees? Okay, if you're saying yes, um, if you know me, I don't, I recognize one of your names. Do you know the eyeball method that I kind of came up with? Okay. I'm going to show you the way I like to do this because personally I find this very confusing on to having to remember each of these. I find this very, very confusing. But that's just me. I don't know about you all. So there's just in my opinion, there's just a much simpler way to do this. So to do it, all you have to do, so first restructure the A, B, and C nodes. Just do that first. So we're going to have 85, 70, and what was it, 90? 99. So now we have some subtrees left over. So here's how I like to think of this. If we need to put if something's going to go to the left of 70, what does it mean based on the property of a binary search tree? It has to be smaller than 70, right? So what nodes, if any, am I going to put to the left of 70? 50, exactly. And then you can kind of cross it off. Or like just put like a check mark next to it or something. Now, if I'm going to put something to the right of 70, what does it mean? It has to be bigger than 70, but less than 85. So am I going to put any nodes over there? And if so, which ones? 80, exactly, because that's the only thing that's bigger than 70 and less than 85. Now, if something's going to go to the left of 99, that means it has to be bigger than 85 and less than 99. Are there any nodes in the from here that satisfy that? No, so nothing's going to go there. And then if something's going to go to the right of 99, what does it mean? It has to be bigger than 99. So what's going to go over there? 100, exactly. Just not like an arrow. I don't know why. I just find that method a lot easier. That's just me. I don't know about you guys. I just don't like remembering the T0, T1, T2, T3 thing. Does that make sense what I did there? Okay. So then you just do a self check. Yeah, no problem. Make sure you do a self check and make sure you didn't mess anything up. So what's the balance factor of 85? Because you always pick up from the node that you circled B. Yeah, it's 0. Good. So we're fine. And that was one more. Oh, we inserted 100 there. So that was another check. Okay. We have two more to go. Two more nodes. Yeah, it's way easier. Alfredo, I take it you didn't have Ahmed then. Just curious. Who did you have for CS1? Just curious. I thought so. Okay. All right, let's keep going. All right, we have two more numbers to insert. So you know what? I can copy the tree and just erase the highlighted. I'm so stupid. Get rid of that. All right. Now we are going to insert. Oh, I forgot. I lost the zero. There we go. We're going to insert 95, right? Yeah, because we inserted 100. So where's it going to go? Left of 99. Exactly. So now start working your way up from 95. What's the balance factor of 95? 0. Good. What's the balance factor of 99? 0. Good. What's the balance factor of 85? 0. No problems. Yes, this would be a full tree. This would also be a complete tree as well. Oops. Whoa, whoa, not this again. Sorry about that. Okay, I'm just copying this tree because we still got to keep going, but I'm highlighting it because they want to see it after that. I just don't feel like circling it. Okay, last up, we now need to insert into our tree 84. All right, so where's it going to go to begin? Where are we going to insert 84? Right of 80. Good. So there it is. So now tell me, which nodes am I going to check the balance factors of? Tell me the numbers. Exactly, Alfredo. 84, 80, 70, 85. As you just start from where you insert it and work your way up to the root following the path. So there's 4 of them. So here we go. What's the balance factor of 84? 0. It's a leaf. What's the balance factor of 80? Be careful. -1. Because it's -1 minus 0, which is -1. What's the balance factor of 70? -1. Good. Because 0 minus 1 is -1. Now, what's the balance factor of 85? 1. Good job. Because it's 2 minus 1, which is 1. So are there any problems? Nope. We're done. There's the final tree. Any questions? How'd that feel to the people who have never learned the ABC method before? And or the eyeball method? Yeah, we'll probably encounter one in the deletion example, Jacob. Yeah, we most definitely will. All right. One more question for the night. Deletion. And you have to use the same ABC method thing. It's just the rules are just slightly differently for traversing. That's all. And here's what we did. So, all right, let's finish this thing. Show the result of deleting the value 8 from the AVL tree pictured below. In the process, there are 2 rebalance operations that occur total. Please show the state of the tree after each rebalance operation. Note after the first operation, rebalance, the tree as a whole will not be balanced. Okay, so let's begin. What is step 1 of doing deletion in AVL tree? Before you check the balance factor, it's a little more obvious than that. Not the children. We're not checking anything yet. We have to do something first. Don't overthink it. See if I can get one more guess. Yes, Evan, you have to get rid of the node. It should always be there. You have to get rid of the actual node you want to delete before you start doing anything. So in this case, we want to delete 8, so kill it. It's gone. So now, remember how deletion works. You do the exact same thing to start. You start from, now you start at the node above the one you deleted and just work your way up to the root following the path. Same thing, except you just don't do the node you deleted because it's gone. And that's it. So now what's the balance factor of 15? -2. Is that a problem? Yes. Now here's the difference with deletion. You still circle the node that has a problem, except now you're going to take 2 steps away from the deletion point. And you want to try to stay on the same level though as the deletion node. Like you go towards the same deletion, the level of the same deletion node, but away from it. So what 2 nodes would I want to circle? 23 and 18. Good job. So now it's the same thing as before. Who's my A, B, and C? Good job, Jacob. A, B, C. So now, first let's bring down what we had. So we had 27, 49, 46, 35, 60, 53, 58, and then 70. And now, from what we had above, B is going to be 18. So that goes there. Then we have 15 and 23. Making sense so far? All right. So now, which node am I going to pick up rechecking on? Because remember, you have to get to the root before you can be done. Which node am I going to restart the checking on of the balance factors? Okay, yeah, technically 27, yes, but it never hurts in my opinion. Real quick, just check 18 first to make sure you didn't mess up. Because if you ever do a rebalance and it's still unbalanced, you messed up. It's a good self-check. So what's the balance factor of 18? 0, so you're fine. Okay, now we're at 27. What's the balance factor of 27? Be careful. It's -2. What's the height of the left subtree? 1. What's the height of the right subtree? 3. What is 1 minus 3? It's -2. So now you circle the node that has the problem because -2 can't happen as a balance factor. So now, remember, we're going away from the deletion point now. So what 2 other nodes am I going to circle? 49 and 60. Now remember, if you're at a split like you are here, always go in the direction that has the bigger tree. So in this case, you go to the right. But imagine for a quick second that this 58 wasn't here and that they were the same height. You just keep going then in the direction that you came from. So I came from the right, so I keep going to the right. Does that make sense? So I would still go to 60 in that case. Okay, cool. Let me get rid of that tape. There we go. All right. So now, who's going to be my A? -27. Good. Who's going to be my B? Careful. Careful, Jacob. Remember, Jacob, A is less than B is less than C. So B has to be 49. A has to be the smallest, C has to be the biggest of the 3, and then B is in between them. Just be careful, Jacob. Take your time on these. Okay. So now, though, I forgot who asked, but now you're going to see the eyeball method again that I kind of came up with. So remember, because you see, we're going to have a lot of stuff left over. as you can see. So remember, with the eyeball method, if you don't want to do the T0, whatever, just first bring over the BAC nodes, those three nodes only. So you'd have 49, 27, and then 60. Now there's four possible things. Yeah, that's what I'm saying. You have all the T's. So now there's four possible subtrees you have to check. If something's going to go to the left of 27, based on the binary search tree property, what does it mean? Everything to the left of 27 has to be smaller than 27. So what would I put there, if anything? Just 15 and 18 and 23. You bring over this whole subtree. Does that make sense? And you keep the order the exact same. Okay. Now do it again. Except now, based on the binary search tree property, if something's going to go to the right of 27, what does it mean? It has to be bigger than 27, but smaller than 49. So what does that mean? What's going to go there, if anything? 35. Good. Just 35. You can't bring four. Oh, wait. Yeah, 46 too. Yeah, 46. Let's go over too. Sorry. Yeah, 46 and 35. Because both of those satisfy that. Both of those are bigger than 27 and smaller than 49. Does that make sense? Okay. Let me move this out a little more just so I have more room. Okay, so we have two more. If something's going to go to the left of 60, it means it has to be bigger than 49, but smaller than 60. So what's going to go there? 53 and 58, exactly. 53, and then you keep the rest the same. And then lastly, if something's going to go to the right of 60, what does it mean? It has to be bigger than 60. So what's going to go there? 70. Good. And now do it. I forgot to check off all these as we did them, but it's all right. You don't have to do that. So now do one more quick self check. What's the balance factor of 49? It's 0. Exactly. Because the height of this is 2, and the height of this is 2. So 2 minus 2 is 0. So that's it. That's the final answer. Does that make sense to everybody? If you want, real quick, for those who did not take the class I TA'd for with Ahmed, before I end the meeting, let me send along your way to aid in your studies. Um, I'm sending out a playlist of recordings from my labs. Feel free to watch them. If you want to look at like when I did questions like this kind of stuff, watch the ones where I did quizzes. Um, those quiz review ones mainly go over questions for the topics. So, any questions on this or anything else in particular before we end it for the night? What's up, Evan? Also, you can unmute too if you guys want. Yes, Sebastian, yes. Also, yeah, make sure you can also look at Google's old CS1 exams too. Again, sorry for some of the mistakes I made tonight. I apologize for that. We're only human. Um, It depends, Evan. I think it's honestly just random. There's like no like you're not. I can't say to you like, oh, there's an AVL tree question on this one. You know for sure there'll be an AVL tree on this one. I think usually they change it if they can, but sometimes they don't. Like the only thing that's guaranteed, like you'll always get a DMA question and you'll always get algorithm analysis questions. But like the format of them could be different. Does that make sense? Like some might be coding, some might test you on like memory space, some might test you on like the math problems versus the recurrence relations, things like that. So it just depends, honestly. You just have to be prepared for literally anything. So any other last questions, comments, concerns, final remarks? And again, I hope you all found this really helpful. Once again, I apologize for the mistakes. Of course, happy to help. Um, we will see you. I will be doing this one more time Thursday. For Thursday's going to be great because I don't have to be anywhere on Friday, and I don't think most of you do. It'll be the same time on Thursday on Zoom again. Be finishing up the rest of the topics, which will be what's left. Where is it? The base conversion is so fun. The only thing I'm not looking forward to on Friday or Thursday is bitwise. I don't like bitwise. So base conversion, binary search, heaps, tries, and hashing and hash tables. It should be a little faster. These two are pretty fast. So is binary search, honestly. Yeah, hash tables are fun. Or as I like to jokingly call them, I don't know why, this is just what when I first heard the term hash table, I thought of them as hash brown tables. And so that's just what's stuck in my head for some reason. So hopefully I didn't make you all hungry for hash browns, but all right. I guess if there's nothing else, I'm gonna yeah, I'm hungry too. I need to eat dinner. Sebastian, are you looking at Ahmed's thing? Like that presentation in the course? The website, the UCF FE website, like one of the preparation ones. Don't worry about backtracking. It's not. It used to be on the exam. It's not on the exam anymore. It's a CS2 topic now. It sucks. It's so tedious. So, all right. Anything else? And AJ, I'll send you the recording again right after in that same folder, and I'll send you the notes and slides again so you can post them for everybody else. So, all right. Take care, everybody. Rest up tomorrow and keep on studying hard. We will see you on Wednesday. Take care, everybody. Thank you.